Good morning, everyone. Thank you for attending this tutorial today. We are so excited to show you different kind of solutions that we have in the open source community for all of your needs, from training to deployment. We have full day tutorial today, and this is the name of the tutorial. Basically, we have age-optimized deep learning, harnessing generative AI and computer vision with open source libraries. We have a great team of engineers that help us to prepare this for you. Some of them are here. So we have Adrian is here, Shuo is here, Alexander, and Raymond as well, and my person, Paula Ramos. So, and Samit, where's Samit? Samit. No, just stay here. You are the famous person here, so it's fine. So we have some people that they were not able to come here, but with their work, we are also able to show you today, not just this content, also some demos that we prepared for you. Ria Cherubu and Shen Fiona Shao and Yuri Gorbachek. So we will have 4 modules today, fundamentals, that we will talk about the first 2 hours today. Let me see. So here is the outline for today. We have the first module, the module number 0 is fundamentals, where we want to show you what OpenVINO is, what OpenVINO training extensions is, what neural network compression framework is, and also some of the amazing things. Okay. So, and also some hands-on experience that we have for you for showing how you can expedite your deployment using OpenVINO solutions. So we have the module number 2 that Samit will have an amazing presentation today where he will explain what OpenVINO training extension is and how you can utilize that for training as well. We have the module number 2, that is the first session in the afternoon. Shuo will talk about LoRa weights for stable diffusion. And this is a beautiful work. And we have the module number 3. So Alexander will help us to close the tutorial today. And with no more words, we will start. Okay, let's start with this. We will start with fundamentals. So we are in charge of this module. And when I say we, this is the evangelism team that we have in OpenVINO. It's a worldwide team. We have 3 evangelists in the US, 2 evangelists in EMEA. We have Anisha in Asia, and we have Shuo and Ethan in China. If you are familiar with these locations or you are living there, so just locate your evangelist and connect with them if you have any questions. So first question for you is, what is the challenge? What is the challenge that you have when you need to run the deployment? So maybe you are looking for the best hardware to expedite the process, or you need to maintain the code with different architectures, having different kind of frameworks. What is the challenge that you have today? So I think that we will have different depending on our sector. Or maybe you want to cut off the AI with some new trends, but you don't have the hardware, and you are looking to expedite this process to optimize and quantize the process and use the same infrastructure. Or you are looking for a new GPU or a new CPU where you can deploy the models faster. So right now, so we are talking about multiple things, and not just conventional AI. So in the past, we were talking about voice recognition, super resolution, pose estimation, like the main challenges that we have. But right now, we are talking about generative AI. And these new things are coming with new challenges as well. So instead to talk about, for example, hundreds of thousands of millions of parameters, right now we are talking about billions and trillions of parameters with generative AI. And that makes the things a little bit difficult because we need to manage bigger models. The inference will run maybe slower in the same infrastructure, and we need to use different kind of hardware. So maybe this evolution of AI is moving our infrastructure as well. And part of this tutorial today is how you can use the actual infrastructure for using these new AI trends. So, and the question mark is how you can optimize, quantize, and deploy your AI solutions. So, and right now, I think that after this tutorial, you will be a superhero, just fighting with those blockers, with those pains that we are talking about, size of models, inference speed. We are talking about also a memory footprint. And the solution in that case that we want to show you today is OpenVINO. Anyone here is familiar with OpenVINO? I'm familiar with OpenVINO. Okay, more or less. What do you think that OpenVINO means? Stand for. Open. Open vision something, okay. Open for open source. V for visual. N for neural network. And O for optimization. OpenVINO is the inference framework that Intel created 5 years ago. What happened 5 years ago? We were talking about visual, but right now we have not just visual. So we have as well NLP, natural language processing. We have audio. We have large language models. We have generative AI, transformers, diffusers. And in this journey that I think that all of us, we are developers. No, we are developers making these things for a while. So when in this journey, we need to have the model, we need to optimize the model, and we need to deploy the model. So basically, we cannot talk about in the industry perspective, we cannot just talk about training. We need to talk about the complete workload that is training, optimizing, and deployment. So basically, OpenVINO help us on this journey. How? Basically, with OpenVINO, we can use multiple frameworks. You could have your model coming from multiple frameworks. If you have PyTorch, you have TensorFlow, you have Keras, TensorFlow Lite, Onyx, or PaddlePaddle. You can utilize that model and use OpenVINO, looking for optimized performance. When we made this conversion, we are converting that model that is coming on those frameworks in something that we call intermediate representation format. That is the OpenVINO format. Basically, we have the architecture of the model in an XML file, and we have weights in a bin file. Basically, the intermediate representation means 2 files that we need to utilize. Good thing of OpenVINO, and I think that this is one of my favorite key features, is agnostic to the hardware. That means that I can write the model once and deploy everywhere. And the good news is this is not just for Intel hardware. It's also useful in non-Intel hardware. We are supporting ARM as well. So as you see here, we have a wide range of support for CPU. We have Atom, Core, Xeon, the new Intel Core Ultra that is part of the AI PC. This is one of the AI PC that we have here today for showing you some demos. Support of ARM. For GPU, we are also supporting integrated GPU. And what is the beauty of that part? If you take a look of your computers, all of you have an integrated GPU. And the majority of you have Intel integrated GPU. Right now, you can use that specific chip for running different kind of AI workloads, not just computer vision, also generative AI. And that is boosting the AI and putting the AI in another side right now, because you can utilize that integrated GPU. So we have Arc, that is a discrete GPU that Intel has. Initially, that was created for gaming, but right now we can use this as well for AI. And we are also boosting the performance with the discrete GPU. We have a version of the discrete GPU for data center that the name is Flex Series, and also Mac series. Good thing, in this device that we have here, the AI PC, when we have the Intel Core Ultra CPU, we also have something that we call Neural Processing Unit, NPU. And that is also boosting the AI. And also we have support for APGA. So agnostic to the hardware, you can deploy these ones, and you can write these ones and deploy everywhere. Different than if you need to, for example, create a model and you need to run that in the GPU, you need to train that specifically in PyTorch for that specific device. Here is a different thing. So moving forward, another good thing is supported with multiple platforms and multiple operating systems. So the people that is not familiar with OpenVINO, we have multiple ways to install. And we have a great tool for the installation. Right now, we have OpenVINO 2024.2. This slide is a little bit, we need to update this slide because yesterday, we released OpenVINO 2024.2. And in that installation, you have two options. You have OpenVINO package without generative AI support or with a basic support of generative AI. And we have another package with full support of generative AI. So you can visit, you can scan the QR code and take a look of how the installation process is, depending on what is your preference, Windows, Mac, Linux, what is the distribution that you are looking for. You will have multiple options in that case. Okay, any questions so far? I want to make a pause here. If you have any questions. Okay. In which kind of use cases we need to use generative AI at the edge is the question. So this is a great question. So imagine that you have LLM, a large language model, in your laptop with your data, and you have your data on structured data, and you need to analyze that data, but you don't want to put that data on the cloud. The security thing is really important in that case, because you can keep your data, the privacy on your data, and you can run that at the edge. This is one example. Another example is an artist, for example, digital artists. They don't want to share the weights of their model, and they want to continue creating this, again, with privacy. We have that option as well. I'm talking about transformers and diffuser in this case. So, and this is just one example. Industry, they want to create a lot of stuff with LLMs, and they have the potential of LLMs in industries, for example, in manufacturing. We have also we have also that option that they can run this in their own devices. They don't need to share it in the cloud. And right now, you could also define when I need to use cloud, when I need to use edge. And this is really important to understand which models we need to use in the cloud. Maybe the bigger models where we need a powerful machine, those that have maybe trillion of parameters. Or at the edge, we can have maybe billion of parameters, or we can use the same model, optimized model with integer 8. I will jump right now after this answer. I hope that I answered your question. To explain how OpenVINO is converting and optimizing and quantizing the model. Okay, so we have multiple methods for optimizing and optimizing and quantized models. So the first one is the model converter. So with the model converter, as I mentioned before, you have your model coming from different frameworks. You have two options. You can use the model conversion through the command line, or you can use the Python API. So what we are doing with that, we are converting from FP32, so 0.32 to FP16. Basically, performance optimization, like graph pruning and fusing some operations. That is the goal of the model converter. And the model converter is a cross-platform command line that facilitates the transition in between training and deployment environments. So the training environment is your Python, Keras, Parrot. And the deployment environment is OpenVINO. And that model converter is helping us to talk in between. And as I mentioned before, the result of this is the intermediate representation format. So here in this side, we have the intermediate representation format, the XML for the architecture and the bin file for the weights. So if we want to see how this is working, it's easy. It's basically one line of code. When I say basically one line of code, so because the conversion is happening in one line of code, so you need to use the object OpenVINO that we have here, use convert model, put the model that you want to convert in the input tensor shape. That's all. And you can save that locally. But what happens if I need to use another kind of frameworks, or maybe utilize some pre-trained models coming from different frameworks? This is the way, exactly the same. So we are just changing this portion in the command line. So basically, we have support for multiple frameworks, as I mentioned before, and we are using the OpenVINO runtime. And I think that one of the things that I really like for about OpenVINO is the easy way to manage the code. In just 7 lines of code, you can run and you can deploy with an optimized model, and you don't need to overcomplicate the code. So I will show you this, how this is working. So you need to import runtime as OB. You need to make your pre-processing stuff for the image, for the computer vision. You need to initialize the core, and over that you can read the model, you can compile the model in the device, and you need to define as well what is the output layer that you have. And finally, you can show the result. So, and just pay attention to this here when you read the model. So, this is not working. So he's asking me what kind of frameworks you are using. PyTorch, TensorFlow? PyTorch, okay.
TensorFlow still?
No.
Oh my God.
Keras? No, Keras, okay. Yes.
Huh?
Like
Anyone use MATLAB?
Love you. Okay, see, this is good because, depending on that, if you are using a PyTorch model, so you just need to modify that line of code and include the PyTorch model there. Okay, so moving forward, something that is really special is take a look of this compile model, and when we are compiling the model to this device. And this is the beauty that I mentioned before. This OpenVINO is agnostic to the hardware. That means that we can use the same model, and the unique thing that we need to do is change the device. So next question is, are you running the deployment on CPU? Who? Who is running the deployment in CPU? CPU. I'm running on CPU. In GPU? Intel GPU. Good. Okay. We have a party. We will send you some invites to the party. Okay. So the next thing is you don't need to change the infrastructure that you are using if you use OpenVINO. Why? Because you can use the same model with different hardware. So if you are using a CPU, you can use the same model with Atom Core, Xeon, Intel Core Ultra, or ARM. No Intel hardware as well. But also we have the support for GPUs. And as I mentioned before, this is a great support. And we have also the new thing coming from the neural processing unit, NPU. And this is another key feature that OpenVINO has, is auto plugin. So who is an expert in quantization optimization here? Yes, he is a principal engineer of Intel. No, no, you. No, I think that this is something that maybe people as Alexander, he is an expert on quantization. He knows pretty well how I need to schedule my process in different hardware. You know, I'm an expert in quantization and optimization. I know which layers I need to send to the CPU, which layers I can send to the GPU. I can split the work and balance the work in between the hardware that I have. And this is also one of the key features that OpenVINO has. We have auto plugin. That means that you don't need to be an expert, and OpenVINO will split that work in between the hardware that you have. And that is great. Auto plugin right now is working for CPU plugin and GPU plugin. And basically, auto plugin chooses a device best suited to the task for the task and configures the device based on hints. You want to create performance hints, latency performance hints, or throughput performance hit or cumulative throughput, cumulative, yes. Yes, thank you. So, and also auto plugin handles the X logic on multiple devices. So that means that also you can set up and schedule multiple devices. So right now we don't have, we exclude NPU in that auto plugin. So the auto plugin is working just in CPU and GPU now, but just stay tuned because with the new releases, we will see how this auto plugin is also including NPU. So let's talk about these performance hints as we can set up the auto plugin. For example, with a latency, if we want to create a performance hints for latency, it is simple. You know, when you need maybe a single stream, you need to inference Y by one, latency is the best. You need to hint the latency. And the way to do that is, as you see in the code, in the command line, compiling is the same command line, but we have a config parameter when you need to say, I want to hint latency. So the next thing is throughput. So, and when I need to use throughput, when I have multiple streams and we need to run inference concurrently, and basically we are doing here an auto batching. Simple as include in the command line performance hints throughput. That's all. So what happens when we need cumulative throughput? So that means that we want to run multiple inferences with multiple devices. Selected multiple hardware, the discrete GPU, integrated GPU, the CPU as well, and also NPU. So we need this when we have multiple devices, multiple streamings, we have inference concurrently, auto batching, and also we need to assign device priority. And this is also great that we could have this in one single line of code with cumulative throughput in the configuration. So how that is working when we need to utilize multiple, for example, multiple GPUs, we need to define the priority of the devices. Oh my gosh. Can you hear me? No.
You know, with so we spent a lot of time actually with customer before designing some of this architecture for the edge use case. So when they're doing that, let's do the coverage right now. By the way, I'm Raymond. I'm also part of Intel. I spent a lot of years in Intel.
Hello. No.
So
Hello. Oh, hello.
deploy anything? Good work. You did? Yeah, a couple times. It's hard. You can try it. It's not fun. We have millions of devices, like all the devices.
Hello.
Actually, is a lot of time when you get a silicon. There, it's too much. Unless you have some provide all the resources. This particular one was really interesting because I use case where people probably a lot.
Something? Yes, it's again.
Perfect.
Where the GPU because they're very good for throughput mode, right? Cumulative means like you want to add up all this workload so that you can actually maximize saying your, your AWS account. Pay by hours, guys, right? So that hour of work, so this is actually what we have done to put it all together. So when you think about architecture at Intel, a lot of these kind of plug-in, all this is designed for you as a developer, especially open source developer, to have flexibility to manage your workload. And you would start to realize the pain when you deploy things is, we have a CPU sitting at 50%, you basically losing another 50% of your money, right? And that's a real problem when it comes to throughput. And that go back to Paula.
Thank you, my lifesaver. Thank you, Raymond. So right now, you saw the code and we will run the demo because we are developers. We need to see the evidence that this is working. I cannot say this is beautiful, this is the better performance that I have seen in my life. No, I want to show this to you as well. So let's run the demo that we have here. We have multiple demos today, multiple demos. This is the first demo, the basic. Let me run this all in once. So
big flash, clap, okay, don't scream. Bigger, yes.
bigger, yes, so hold on. More.
Hide the left.
Uh-huh. Okay. Let me show you something. Okay. Can you see the performance there? I cannot make that bigger. I mean, in numbers, yes, but no in size. So have you seen that before? It's running in 1,000 frames per second in this machine, in this laptop. It's a post estimation, I don't know. It's running CPU. Let me change the device and we will see how the performance is changing. We are using an optimized model as well. I want to show you how the code is working, but I also invite you to visit OpenVINO Notebooks repository where you can repeat this work on your laptops. So we are running this in the AI PC where we have the Ultra Core 9 or 7. Ultra Core 7, so we have Ultra Core, Intel Core Ultra 5, 7, and 9. This is 7. So imagine that you will have better performance if we are using in Intel Core Ultra 9. Also, we have another kind of devices. This is a laptop, but also we have these AI developer kits that we will have a small computer where you can also run these, for industry solutions, or if you are a practitioner, you want to try something. We made a workshop yesterday. So this is the device. This is the device with the same chip that is here in this laptop. Okay. So let me change the device. So right now you can see here that we are making a lot of processing, a computer vision process as well. Basically here we are calling the model that we have human pose estimation. This is FP16 integer 8. That is coming, oh my God. That is coming from a model that we have in Intel. That is a pre-trained model. I don't know what is going on. How you fix that? Just moving cables? Okay. I hope that you can listen to me. So right now we have here also, just the path of the model and all. We load the model. We can see the devices that we have available, and we were using auto, Raymond. We were using CPU and GPU. We are also auto plugin. So we have CPU here, we have GPU, so we have NPU and auto. Let's do that on GPU. Okay.
Yep. Sorry guys, technical issue. Anyone know how to fix mic here? Nope. All right. I'll help her a little bit because I project my voice bigger. Anyone knows how to do quantization? No, right? But you saw here, we're actually running a quantized model here. So this is one of the very early model I started using when I was in Intel back in those days, I'll say. Because it actually 4 years ago, I can get this up to 60 FPS. I was like, yes, right, 60 FPS, because that was what you saw in internet back in old days, remember all this post estimate. But what you're seeing here is how we are fencing these kind of trajectory over the year with this open source approach. Anyone use OpenCL? OpenCL, anyone know what OpenCL is? Yes. So this is one of those where under the hood, you can see we actually help you to parallelize this work. So at runtime, we're actually compiling the kernel, so you don't have to do all this work. If you anyone have done like OpenCL programming, you have to like configure all this, and this is what we have done here. You want to project it, please? Okay.
No, I'm okay. Yes, for sure. So we are running there on the GPU as well. And this is the integrated GPU. We don't have discrete GPU in this machine.
Yep. That's method, yeah. So this is almost like a hidden secret in the Intel processing unit. Those like CPU usually come with this bundle. And they actually have a shared memory as well with the CPU. So sometimes you may find very interesting performance. Let me see it, yeah. And you open you make it bigger. And then you can show not the 3D, so we're not doing 3D, but we're doing compute. Yeah. If you go to the engine, under the GPU, all right, I'll point for you. All right, and this is actually very interesting because it took me a while to figure out here, the 3D compute. So you can see that actually, this is actually the compute engine behind it. And this is a very lightweight model. Of course, it's like, right, I've seen this many times before, many years ago, but that's how we get started, right? We actually start with some of those very interesting model that you saw, maybe a couple years ago, remember CPPR, we still call it deep learning, and then today it's still with Gen AI. So this is actually the evolvement, right? How we actually utilizing some of these silicon to do the acceleration. All right.
Okay, no.
Because it took so long to run this before. And now today actually it's very easy to couple line of code to get started.
Do you have any questions so far?
You
Okay.
download this? Yes.
Is there any loss in accuracy or?
Very good question. There's an expert here, we can tell you more, but I can answer some of the easy part. So when we think about the tooling, right? The tooling is when you're trying to compress this model, you're trying to figure out, get to this target, right? So we have different mode to like gauge like how much accuracy loss we are looking at. Again, I'll leave the expert later, but the easy way to think about it is you usually calibrate with a data set. So you have to have some knowledge about, let's say when you're running, let's say this inference task, which like some of the sample example you put into, let's say it's object detection, give it some cat photos, okay? I'm trying to get the cat out. Right, and then from there, whenever, I think there's like different layer when you're trying to quantize, there's like different way of like quantizing it more aggressively or just like want to preserve more accuracy. Because I remember correctly, some of the conversation with the engineer, they said that some of the layer is very sensitive if you quantize it, right? Some of it less, right? So that's all the tooling behind this. It's called NNCF, right? And this express right here, you want to tell a little bit more how NNCF works?
So we have a quite sophisticated method. They can fit.
We talk about
Yeah, so.
Yes, no, is there? Let me take this out. Just push it.
yes. Stand up, Alex. Okay.
It's not working. Yesterday was exactly the same problem in the anomaly workshop, exactly the same problem.
So we can like keep this stuff, recognize this stuff, that blocks stuff. Recognize like, for example.
Could you move the cable? Move the cable.
Yeah.
I cannot see the cable.
So it doesn't. So we but with this, so we can quantify per day. And of course, it's like very custom model, so.
No.
API visualization
Huh?
function and automatically like finds the layer inside the model. Quite a lot of capability. Thank you.
Yes, sorry, yeah.
So if you don't use this model conversion, what would be the inference?
We can try it. But do they have it? I don't know. I can show you usually. There is no original model. They don't original model. But usually is a performance gap based on a few, right? So their first answer to that, because first depending on the hardware. If you're using Xeon, we also have some built-in power acceleration on innate. So we have put DNNI. What's the vectorized neural network?
Yeah, it's extension.
Extension.
Yeah, 8-bit extension.
8-bit extension. So when you do the 8-bit, it's not just like, big and smaller, but we also have customized hardware to have the pipeline to get that multiplier together. So you may get like 2 to 4x depending on it. But fundamentally, when you're reducing the memory footprint, and then in it is a lot easier. So on average, again, the formula that usually 2 to 3.
And in the second demo, I will show the difference between PyTorch and OpenVINO. So
and also the
PyTorch is running on CPU, yeah. So I will show the difference between PyTorch CPU, OpenVINO CPU, and then OpenVINO GPU.
And then also the NA. We have all this benchmark. Oh, we have a benchmark website.
We have.
Yeah. So you can see those number on the where is it? OpenVINO.ai.
OpenVINO docs.
Yeah.
And then on the left there is a menu bar, and you need to find performance benchmarks. And then
That's really hard to find sometimes, but it's there. Yes.
I have a question. Are those also run on DPUs? So does that also run on DPUs, the model? Say
That one just ran on GPU, yes.
DPU, not GPU.
BPU, NPU,
What's a DPU?
So it's a deep processing unit, right?
MPU.
it's called neural processing.
neural, neural.
It's
Yes.
a very new term because back in the list for the DPU as well. So the visual processing unit.
But everyone has it, like Qualcomm.
Yeah, look,
Apple.
even my t-shirt, I have it called GPU, they kind of rebranded it as like, oh my god, my t-shirt has to be updated. To be real, guys, like sometimes I can catch it. But it's the same thing to me, right? To me, it's a piece of silicon that are very good at doing parallel processing. Talks to me. All right, let's go back now to the blank page.
I think we still have.
Docs.
Yeah, one more question. Yes, of course, I think. Yep.
Service, what do you mean, like online service or like the functionality?
I mean, the concept.
Yeah, we have it.
Just wait until this talk. I try not to see this thunder.
I'll show the demo.
Yeah.
You
So-
can run it.
Alexander talks is at 3 p.m. today.
Don't go yet, okay? But
3:30?
definitely stay now.
Okay. Yes.
I think
Around
most
3:30,
important
3:30.
Question for him later is, for Gen AI, we have all the myth, right? Remember, people say quantize it to in 4, not even in 8. And then 2 bits, I think that's recently have some paper, 1 point something bit.
Only one.
1 bit.
One, how does it work? I have no idea. Ask this person, please. So that's the whole point why we're trying to bring the expert to answer some of this really. But how can we get this hardware to perform very well on very, very large model? Because we know what trillions of parameters at one point. All right, back to you. Is the
No,
mic
it's
working?
no,
tried
it's
it.
not working. So I think that we need to scream the whole day. So
Closer, if anything, guys, like,
Um,
otherwise you lose your voice by the end of the day, yes. Yep.
So this is only a basic question.
Yep.
Is OpenVINO, open source version of NVIDIA's TensorRT?
Absolutely not.
I'll leave that as a,
OpenVINO is open source.
Yeah, it's open source,
It's
yeah.
full source.
yeah.
We even don't know how it works.
Because we cannot compare with that. But I think we can also think about from a user perspective is this is the competitive offering for you to get acceleration over here. Yeah, I think that's the answer. Yeah, from the user perspective, but the internally, I would not comment.
OpenVINO does work on NVIDIA GPU.
Secretly, yeah, you can try and contribute. We have a plugin. So we do have a plugin that actually, we have a third-party contributor made it happen. That's why we're here today. The reason we have open source is we want to be the supporter of this community. We don't like, hey, close it down and good luck. You know, this actually been around for many years, and we run Google Summer of Code as well, teaching students how to write applications. And then these are all under Apache Day2, so you can commercialize it. So you know, have any strings attached.
There's
Alright.
another question there.
One last one. We have to keep going. Yes.
Slightly different ongoing conversation,
Yeah.
but do you also have an equivalent or a similar API for native C or C++ applications?
Yes. Yes. Documentation again. Right
So we
there.
have also support for C, C++.
It's perfect.
Started there.
That's how we started.
Yeah.
It's actually the first thing I'm trying to read. All the source code, you can go on the GitHub. You can look at the first release. It's not even called OpenVINO. It's called
CV,
something SDK.
CBSDK.
Pretty part of that. Yeah. I read the source code. It's pretty interesting.
Mhm.
It's pretty simple. It's
So,
fast.
last question there, and that's, okay.
Do you support web,
WebAIM
WebNN?
or
JavaScript
API?
WebAssembly or WebDP?
JavaScript API.
Yeah.
Yeah, we have
Okay,
JavaScript API. We have
And do you have the same kind of speeder?
I never tested that, so I'm not sure.
He's very honest.
You or there are two pieces. One is like JavaScript, but
Right.
anyway, like we run on the
Right.
native hardware,
Right.
and another piece is like WebAssembly, and everything like executed in the browser sandbox. So we have some version for WebAssembly as well, but it's not like super optimized.
Yes, it's good.
So
Yeah, the
it's very
conversation,
good. Some
so.
customers like
Mm.
industrial customers. Yeah, it's a new thing, right? So we work with that.
Sit here. Sit here, Alexander. Please. All right, it's too shy. Okay, all right. All right, let's continue.
So
Sorry,
let's
it's not
continue.
Agenda of like topic, want to make sure that you learn something out from this. The learning is really about you can do the work, not like, oh, here it's great, you know, but you can bring all this home because the whole way we structure is open source. for you.
So have in mind that during the day, we will see, so now we are looking just for some fundamentals, and we will see deeper these kind of topics as well during the day. So Alexander talk is at 3:30 p.m. So right now we'll talk, the next speaker is Adrian. So he will talk about software optimization, some theory about quantization as well. And then Raymond will talk about hardware optimization, and then Shuo will close the fundamentals part. Okay, thank you so much.
Good, thanks, Paula. I hope you can hear me from the back. If not, please come closer.
Make sure you still talk.
Yeah, I'm talking, but it doesn't work anyway. So, yeah, of course. Paula showed us some basics about OpenVINO. I would like to go deeper to some software optimizations we have already there. Some of them are enabled by default. Some of them have to be enabled by you. So I'm going to cover them, and then I will let you know which of them are enabled by default, which of them you need to enable yourself. Let's start with auto batching. So we are back to the throughput and cumulative throughput mode. So in this case, of course, we have many infer request queues for our processing units. And auto batching means that we will batch your input automatically. So it means that when we have the first data, like image, we are on conference, computer vision conference, right? So we have first image, then we don't do inference immediately. We wait for the second one, we wait for the third one, fourth, and then we do the inference with all of these inputs. And then again, the second batch, once again, second, third, fourth input, and then again, inference will be done automatically and batching will be done automatically. So of course you can specify, maybe I will talk about that on the next slide. So here, how to enable auto batching. It's enabled by default. So if you go with performance hint equals throughput or cumulative throughput, it's enabled by default. But of course, we have some control on that, so we can, when we look at the code, yeah, it's enabled here by default, and then we can of course change some parameters like how many number of infer requests it should have. We can specify to optimal number of infer requests, which should be also specified by default, or we can go with our own number, for example, 4, right? So we know that, for example, the device is capable to take 8 requests at once in one batch, but we would like to save some energy or some utilization, anything like that. So we specify that we go just with 4 inputs for a batch. So, and it will be batch automatically. So this was the first thing. The second thing is default inference precision. And this is super cool thing because if you even have your model in some specific precision like floating point 16, floating point 32, and so on, we will change this precision when we run the inference. And why? Because in some cases, like CPU, especially Xeon CPU, we will use bfloat. So you cannot convert your model to bfloat like explicitly. We will do it implicitly in the code when you run the inference. So bfloat is a faster version of float, of course, because of some... Huh? Yeah, do you know what bfloat is? The name is brain float. So it's like a floating point 32, but we've removed some bits of mantissa, right? So the explanation, yes, explanation is the same size. So that's why it can capture the wide range of values, and at the same time it's faster to compute because we have less bits.
A little bit more rounding error, if you think about it, right? It's like
Yes.
cap the precision.
Yes, exactly. So
when you're training things, doing inference a lot of time, you don't need that 0.00001.
yes.
Looks like you have other error from the sensor, other error from everything else.
Yes, that's the solution for CPU, especially Xeon CPU. So in case of GPU plugin, the model will be automatically converted to floating point 16 because GPU support this precision best, and the best performance comes from this precision on GPU. When we have NPU plugin, it's also floating point 16, so it will run on an NPU device. And for the future, when we have the next version of XPU, whatever, X means unknown right now, right? It can be MPU, APU, whatever, right? It will be converted automatically to the best precision for that specific device. And this is enabled by default as well. Then we have thread scheduling. So usually in the latest version of Intel CPUs, starting from the generation of 12, we have P-cores and E-cores where P-core means performance core and E-core means efficiency core. And we can use both of them for inference, but we also can change that behavior. So we can change that to P-core only, for example, or E-core only, and we can enable hyper-threading for P-cores, so we have more logical threads. What is related to that? It's called, it's also related to threads. So in this case, some threads are assigned to specific layers. So in this case, when we have a model with layer 1, 2, 3, first 4 threads are assigned to these layers. And even if we run the next infer request, let's say at the same time in asynchronous mode, it will use the same threads. So in this case, we are competing on the same device, even the next 4 threads are just idle. How to change that behavior? We can set enable CPU pinning to false. So in this case, the next 4 threads will be used, but at the same time, there is one drawback. We have no guarantee that the same threads will be used across layers. So in for the next layer, different threads can be selected to run the inference. The next thing I would like to share is shared memory. Usually, OpenVINO is a C++ library with Python wrappings. So in this case, when we use it in Python, that the default behavior was previously to copy the data first. So when we run in with a NumPy array, then we copy that data. We have a C++ buffer, and we then use that copied memory to run the inference. But we changed that behavior, so this is also enabled by default. And right now, it's sharing, not copying. So we are sharing the same memory. You just need to be aware on that if you run asynchronous mode, because you cannot change the input before the inference ends. Otherwise, you will mess up the inference. The next thing, model caching. So caching is disabled by default. So when you read the model and then compile the model, it takes some time, right, to compile model, especially for GPU, because in GPU, we use OpenCL kernels to provide the inference engine for GPU. So if we enable the model caching, then we spend some additional time to export this cache to disk. But with the second iteration, it's much faster, because what we do then is just reading the cache. So we don't have to compile the kernels again. How to enable this? Just one line of code. So if we look at the code, of course, we import OpenVINO, create the core object, and then we set property cachedir to some specific path. And this directory will be used for cache. And then, of course, we continue with read model, compile model. And in this case, when the cachedir is set, compile model will export those kernels to that cache. So it will be faster in the next round, the next inference. Then optimize processing in many cases. I think maybe in all even cases, we need to do some pre-processing before running the inference. Like, resize the image, divide by mean, and so on and so on. Then we need to do post-processing. For example, if we do object detection, we have some raw results from the network, then we do some non-maximum suppression and everything like that to just return boxes. So the inference is done on CPU, GPU, NPU, whatever you prefer, but pre-processing and post-processing, usually done in OpenCV for computer vision, is done only on CPU, right? So this is a little bit challenge, let's say, because we could run faster. So how to do it? We can include the pre-processing and post-processing into that inference graph with our pre-post processor. So again, we import OpenVINO, then we import pre-post processor. We create core object, read the model, and then we create pre-post processor object with that model and set up format of the data. So we expect images in int8 format with dynamic shapes and with the layout of batch, high, width, and channels. And then we add this pre-processing. So we would like to convert that image to floating point 32, apply a resizing algorithm, then use the subtract mean and divide by scale. And then we will build that into the model, and this new model is ready to be compiled and run the inference. So when we look at the diagram, it looks like this. So we start with some imports, of course, and then we add additional nodes to the graph. So for example, conversion, another conversion, but this is color space, not the precision, then resizing, then subtracting mean, scaling, and then we have our previous model starting with convolution, for example. The next thing, asynchronous mode. So probably you know the term synchronous, asynchronous, right? So in this case, synchronous means that we transfer data to some specific device, let's say GPU or NPU or whatever. Then we do the inference, and when the result is ready, we are starting with the second round, so the transfer, the second data, and so on. But meanwhile, the device is in the idle state because it's not used for that time. So we are just, let's say, wasting the processing power of this device. So we can do it better with asynchronous mode when we transfer the first data, then run the inference. But meanwhile, in the same time, we are transferring the second data. And then when the device is ready, we do the second inference. And in this case, the second result is available much earlier than in case of synchronous mode. And again, let's look at the code, how to run asynchronous mode with OpenVINO. So what we need to do to import OpenVINO as usual, then we load and compile model. I just skipped that part here because it's obvious, right? I hope you can go to previous slide and see that if you are interested. Then we get the handle to the input layer. We define some callback for post-processing. So when we have it back, the result, we need to run this callback to do some post-processing, let's say some boxes from raw results of the network. Then we create infer queue. It's asynchronous infer queue. It's created with the compiled model inside. And then we set that callback that it should be run after every result. And then endlessly, let's take the next frame from the camera. And then let's start async, providing that frame to the inference. After all, we of course need to join all threads, so we need to wait for all. And in this case, of course, we are running asynchronous mode. So I already showed you some additional optimizations. Some of them are enabled by default, as I mentioned, some of them are not. So asynchronous mode is not enabled by default. You need to do it yourself with this code I presented. And right now I would like to switch to the next section, very important section, because we already showed you OpenVINO, like pure OpenVINO code and so on. But it's not the only solution. OpenVINO here is in the center because it plays central role in running AI inference. However, you can use OpenVINO as a pure approach, which was already presented, or you can use OpenVINO as a backend in Hugging Face with Hugging Face API, PyTorch, or ONNX runtime, and to be able to run on any device like NPU, CPU, and GPU. So let me go into details. So let's start with PyTorch. I think, yeah, you raised your hand that you used PyTorch already. So if you use PyTorch 2.0 or newer, you can change the backend for the inference. So in this case, you have your PyTorch code. You don't want to change anything. You don't want to convert model to OpenVINO or anything like that. So what you need to do in this case is just to add these 2 lines of code. Of course, you need to install OpenVINO first, right? But then you need to import that OpenVINO torch package and then use compile function when you specify that backend must equals OpenVINO. In this case, OpenVINO will be used for all operations except those not supported, but not a problem at all because not supported operations will be fallback to the PyTorch again. So in this case, it's let's say a free lunch, I would say, just 2 lines of code, and you can try running with OpenVINO backend. It should be faster, and you don't have to change your code base. You are still with PyTorch model with your PyTorch code. So that was OpenVINO as a backend for PyTorch. Then let's go to the ONNX. In this case, we will use OpenVINO as one of the execution providers. So what we need to do first is, of course, install ONNX runtime OpenVINO in case of Linux. In case of Windows, we do also need to install OpenVINO itself. So ONNX runtime OpenVINO plus OpenVINO. And let's look at the code. So the code looks like this. So you import ONNX runtime, then you specify the device and precision you would like to use. Then you create inference session when you provide that provider, OpenVINO execution provider in this case, with some additional options if you, of course, device option, then do the pre-processing and run the inference with the session. So this is all what you need to do in case of ONNX runtime. Super nice thing. But I think what is the most exciting thing is integration between Hugging Face and OpenVINO. How many of you already used diffusers or transformers? Yeah, some of you, at least
Here, GenAI stuff.
half of you. And what we did, we combined the convenience of Hugging Face with the efficiency of OpenVINO. So there are also just a few changes in the code to run OpenVINO with transformers or diffusers API. I think this is super cool. And I'm gonna show you the code as well. So first, of course, let's install OpenVINO. We always install OpenVINO, right? If you want to use it. Then what we need to do, we need to just replace 2 lines of code. The first line is, of course, import. So we replace the auto model for casual LM. In this case, from transformers package, we replace with the OpenVINO model for casual LM from Optimum Intel. Then we import auto tokenizer pipeline from Hugging Face transformers, specify the model we would like to use, and now is the time for this next replacement. So we use that class, OpenVINO model for casual LM, and we create the model in that class. So it means it will run OpenVINO backend instead of PyTorch or TensorFlow backend. Then usual tokenizer, pipeline, and let's run the inference. So just 2 lines of code to be changed, in this case, to use OpenVINO as a backend with the convenience of Hugging Face API. The next thing, if we compare Hugging Face to OpenVINO, what's the difference, right? So in case of model support, there is no difference. Let's say we support many models, and if the model is supported in OpenVINO, it means it's also supported in Hugging Face. Almost, of course, it must be implemented in Optimum Intel. API, with Hugging Face API, you can use Python, with OpenVINO, additionally C++. Model format in Hugging Face can be source framework like PyTorch, TensorFlow, but it can be also OpenVINO, the model which is already converted. In OpenVINO native API, it should be OpenVINO. And then what else? Inference code, Hugging Face on the left, custom inference pipeline on the right. So you cannot use Hugging Face pipeline in pure OpenVINO code. That should be obvious, of course. We have many also dependencies of Hugging Face, right? There are many of them. When I install Hugging Face, I can see so many packages with my pip freeze. In case of OpenVINO, it's very lightweight. We just need NumPy, maybe a few more packages. This is just what we need. And of course, I'm gonna skip the next rows and go to the performance. Of course, when you run with Hugging Face, its performance is good. In case of OpenVINO, will be best. Okay, because when we convert the model ourselves and we use our own pipeline, there is no overhead on some Hugging Face stuff. That's why. But feel free to use OpenVINO integration with Optimum. How to export that model to OpenVINO then if we run with Optimum Intel? So we can use command line interface and run Optimum CLI tool, export to OpenVINO some specific model. Then we provide also directory where we want to export to, or we can use code. So import the model and then use that code I showed you before to create the object model from the name using that class. And then we can run, the first was related, is it working? Yeah. So the first one, this was related to that one. So if we already exported that model to this directory, then we can use that model ID. Here we can just put the directory name and import in Hugging Face. In case if you want to export from Python code, what we need to do is to provide additional parameter export equals true, and then save this pre-trained model to some directory like OpenVINO model. And it's time to show you how it works. So I'm going to show live demo once again. So I'm gonna use one of the generative AI models, which is called latent consistency model for generating images. So I'm going to run the code right now. What's important here? We, of course, import OpenVINO. We create core object. We list all available devices. There is a Intel Core Ultra 7, that's the CPU. There is Intel Arc Graphics GPU, and there is NPU Intel AI Boost. So we have 3 devices to run here. And then we start with the PyTorch version of this model. So this is the model. This is the model name. I hope it's visible. LCM. And what we are going to generate is a line art drawing of Seattle. And it took, we are going to use 4 steps. It took 14 seconds to run with PyTorch, and the output is quite nice. I like this image. But let's look also what's the difference between. You don't like?
It's fine.
Okay. He also likes. That's good.
Try
Okay.
again. I
Okay.
think it's important to know this, like, only last year this time, this took 10 minutes to run.
Yeah.
More than 10 minutes to run one single image.
Even in PyTorch, right? Right now, 14 seconds. Yeah.
So, but this is like a really big improvement over just 1 year, especially at Intel, because last year when this kicked off, everyone had to say, hey, I need to buy a powerful GPU to run any generative AI things, right? And this is amazing because two things happen. One, of course, people will figure out how to do things more efficiently. The algorithm changed. So this is called the LCM model. It's a lot more computationally less intense. Second is we update our library a lot. So the GPU plugin actually, we spent a lot of time in the beginning. It was almost like 4 times slower when we first released. In just like every 2 months, we've been updating the driver, even down to the driver level to make this support. So a lot of headaches to get it working, but today you're benefiting from the headaches. So if you use that today, I think it's very good example.
So let me show you the difference. 14 seconds in PyTorch. Let's scroll down to OpenVINO. In this case, we are using CPU, just CPU, the same CPU it was used in case of PyTorch, and the running, of course, we are using the Optimum Intel here, so we are running OpenVINO latency consistency model pipeline, and the processing time is 7 seconds. So it's twice faster than PyTorch was, right? Of course, the image is a little bit different because we didn't fix the seed, so it's another seed, so another starting point. That's why the image is different. 7 seconds PyTorch to comparing PyTorch to OpenVINO. But let's also run the next version with GPU. So I'm going to change the device to GPU and start running from this cell. So in this case, we are compiling all models to GPU. Then, of course, the compiling time and the first inference, mostly compiling time, could be longer because we need to compile OpenCL kernels. We don't have cachedr here set, so we need to wait a little bit. And then the performance should be much better. Look at this. It was 1 second. I wouldn't say 1 second. Maybe it was 2, right? Just 1.9 or something. Let's assume it's 2, but let's compare. Let's look at the result first. Maybe it's still a very nice view, right? And 14 seconds in PyTorch, 7 seconds running on the same CPU with OpenVINO. And if we use GPU, and this GPU is integrated into the same chip, right? It's not a discrete GPU card here. It's just 1 or 2 seconds. Super cool, isn't it?
Yay. Guys, it's hard to put it up. All right, thank you.
Okay, let's continue. So what else we have as where we can use OpenVINO as a backend? The next thing is Triton Inference Server. So usually in this case, you need to install Docker, then prepare model repository, and so on and so on. But in this case, if you want to use OpenVINO as backend, in this case, you need to download and convert model to OpenVINO and provide a config pb.txt file. And in this case, it will work with PyTorch, TensorFlow, and ONNX, and then run Triton Server Inference server, yes, and then run client for inference, and you will get the Triton is from NVIDIA, but we also support with OpenVINO as a backend. For now, it works only with CPU and with Linux, but we are working to improve that to support more devices and more operating systems. And that is all for the section of OpenVINO as a backend, let's say. And then we are entering the next section of the optimization, quantization. So this will be covered more during the session of Alexander at 3:30 starting time, but I will cover some theory behind the quantization. So this is a continuous function, a sine function, right? So it can have any value between -1 and 1. exactly any, right? So there is infinite number of values for that. But if we use the quantization, it will look like this. So in this case, we just selected 11 different values for that. And so we said that for any x, the value must be one of the 11 selected. Is it similar? It is. Maybe it's not very similar in this case, but come on, we just selected 11 different values. What if we select just 100 or so? It will be very, very, very similar. Not the same. Of course, it's not longer continuous function. It's a quantized function, but it should be similar enough to be able for us to understand what this function means or does. But if you still don't know what I'm talking about, let's talk about color quantization. We have 3 images here. This one on the left is a image 24-bit image. So every pixel can have one of out of 16 millions of colors. This one in the middle, one color from the 256, and this one on the right, one color from 16 different colors. So we can assume that this is like AI models. This one on the left, it's like floating point 32 models, like, you know, many different values we can use. This one in the middle is like int8 model. So we have 256 different values. And this one on the right is very, very quantized. So we can just select one number, one value from 16 different values. And this one on the left, yeah, it's very smooth and so on. This one in the middle, could you see any difference? I can, right? But there are very, you know, negligible differences, I would say. You still can understand the concept, right? You still see what's on the image. You still see that there is a man standing in the middle of the forest with some sunset in the background and so on. This one on the right is compressed a lot. Maybe it's not so simple to see that, you know, it was a sunset in the background or anything like that, but still a man standing in the forest and so on and so on. So in the case of quantization, we should consider it like a loosey compression. We are losing some information, but maybe it's still similar enough that we can use without much accuracy drop. So this is what I would like to prove here, that it will be work like this in case of AI models. So quantization, the formula, the simplified formula is that we need to change from floating point 32 precision and value range to int8. So we have only 256 different values. So what we do, we just clip outliers because we don't care about them. We don't want them to change the value range for the quantized version of the model. And then we round our values to some specific integer. It doesn't mean that we should round, for example, 0 to 0, or we should round something which is near to 2 to 2. It can be like we are rounding 2 to, let's say, 100 something, right? So we are capturing the range, the dynamic range of this values we have here in our network, in our weights, and we are converting them with this formula to the int8. And quantization, as I said, is a loosey compression. Right now, we are losing some accuracy here. We are losing some precision because we cannot unround these values to the same state as it was before. So when we look at the dequantization, we need to go from int8 to floating point 32 format. And in this case, it's just like this conversion, right? We don't know if we rounded 1, if we rounded 2, or what. We just rounded. So we know that's why there is little accuracy drop in this case, right? Because it's a loosey compression. So let's start with the first type of the quantization, which is not a real quantization. We call it fake quantization. And it means that the fake quantization nodes does the quantization and then immediately dequantization. So the input is floating point 32. Then we do the quantization, immediate dequantization, and after that, we still have floating point 32 out of this node. And the question is why we do that? And the answer will be in a few slides. So first, I just wanted to show you that we have fake quantization. Then the first real quantization is weight compression. So we have our model in floating 32 format, then we train this model, then we have train model, and then we do weight compression. So we end up with int8 quantized model. So all weights are quantized to int8. However, no operations. Only weights are quantized to int8. So when we run the inference with the model which is quantized with weight compression, we need to dequantize that model back to the floating point precision. And then if we add to this algorithm one more thing, a representative data set, sometimes called calibration data set as well, we then will use post-training quantization. And we need those data, that data, to capture the range of the values between layers. So then we can also use int8 operations in the graph. So not only weights are quantized to int8, but also operations are used in int8 precision. So we end up in fully quantized model, and this model doesn't have to be dequantized during the inference. But when we do post-training quantization, I showed you it's a lossy compression, right? So there may be a situation that we are losing some accuracy as well. In most cases, it's a negligible thing. It's less than 1%, really. But in some specific fancy models, let's say we can lose more than 1%. And let's say we cannot afford that. So in this case, we can go to accuracy control quantization, where we add two more things: maximum drop, accuracy drop, or F1 score drop, or anything like that. So let's say we can afford just 1% or 0.5% of accuracy drop. We specify that. And then we also specify validation data set to measure that accuracy. So we are measuring the accuracy before the quantization and after quantization, and we compare them. If the drop is higher than the specified one, we need to not quantize some layers. So we leave some layers, especially sensitive layers, for quantization in original precision, like for floating point 32. So this is accuracy control quantization, but it's not like ideal thing, right? It's not perfect thing. In this case, as we don't quantize some layers, the performance is worse than post-training, that in case of post-training quantization. So let's say that finally the accuracy is okay, but the performance right now is not good, right? We not quantized too many layers. What to do in that case? We need to go deeper. It was so nice animation. I skipped that. Look at this. It's super cool, right? So we need to go to the model which is on the beginning of this pipeline. So we are right now before training. And what we are going to do is we are going to run quantization aware training. So we have our model, which consists of some nodes, like, of course, there are inputs, there are weights, we have convolution and ReLU. And what we do here, we add fake quantization. Finally, fake quantization, what I showed at the beginning. Why? Because fake quantization will run quantization and immediate dequantization. So it will generate quantization error during the training, right? So this error will appear in the loss at the end. And then with our algorithm for training and backward pass, we can fix it during the training, right? So during the training, we are training the model to have it better generalization. And at the same time, we are fixing also quantization error. So then after that training, we can just quantize model without any accuracy drop. Of course, it's not the first choice. It shouldn't be the first choice because post-training quantization should be the first choice because it's the easiest one, the easiest to run. You don't have to have data, training data. You need to have some data for calibration, right? But you don't have to have huge amount of training data. You don't have to have a training pipeline. Maybe you just downloaded the model from the internet, right? So you don't have access to that. So in this case, it's a good thing if you have access to training data, you have access to training pipeline, and you have enough time and money to retrain
Just
the model. Yes,
A lot of time, guys.
and there is a question. If we run forward pass, it looks like this. But what if we run backward pass? What to do with gradient with these fake quantization nodes? And what we do nothing. We just pass it through, right? So it doesn't change our gradient. There is nothing to train, right? It's a simple algorithm. We are not going to change any weights there inside that operation. So we are just passing through. And that was the theory of quantization, some of quantization types we have in our NNCF framework, neural network compression framework. And it will be covered more by Alex in the module number 3. So the last module today. But if we have the model in one of these frameworks, TensorFlow, PyTorch, OpenVINO, or ONNX, then we can use one of these algorithms from NNCF, and then our model will be compressed somehow. It can be filter pruning, so we have less filters. It can be quantized with post-training quantization, our training or weight compression, anything like that. But what you should remember that NNCF is for compression. So this is a part of OpenVINO toolkit, NNCF, and it's used for compression of the model. So to use it, pip install NNCF. And if we compare, if we look at the weight compression from NNCF and we compare some models, especially large language models here like Llama 2, Dolly V2, Red Pajama, and so on, we can see that we are decreasing the size of the model with quantization. So floating point 32, 10 gigabytes in case of Dolly, and 8, of course, we are changing the precision from 4 bytes to 1 byte, right? So it should be 4 times smaller, and it is, right? And let's look at the metric here, perplexity. It's increased a little bit just. So maybe we can afford that, right? So we just change the model size 4 times, so it's easier and faster to download from the internet, for example, from our server, anything like that by the user. But the perplexity doesn't increase a lot. Of course, we can go further with quantization to int4 and so on. So the perplexity increases more, but at the same time, we are changing model size, decreasing the model size even further. In case of Llama, similar thing. The most size saving space, disk space comes from the quantization from floating point to int8. So from 25 gigabytes to 6 gigabytes with just 1/100th of the perplexity increase. So this is also not only disk space, this is also significant reduction in RAM usage, right? Because in RAM, in memory, we just store ints instead of floats, right? 4 times less. And
Question. What's perplexity?
it's a metric for yeah.
1, 2. Alex have to explain this one because it took me a while to figure out what it means. Because like in computer vision, you can like matching a cat, yes or no, you know, plus and negative.
Yeah.
But this is non-trivial because we talk about language.
Yeah.
About the next token to generate, right? How do we measure that? So Alex, do you have any answer to that?
Just in a nutshell, just a discrepancy between the 2 sentences. Yeah, so like the lower is better.
But why do we talk about increase then?
Because we are
The
changing.
lower is better.
Yeah, so we are changing the precision. Worse. Yeah.
So
Yeah.
this increase means just, okay.
Yeah, so of course, if we quantize, we have some, let's say, accuracy drop. So we are increasing in perplexity, right? Perplexity, in this case,
I can't even say the word correctly. Perplexity?
perplexity?
Okay,
Perplexity,
good.
yes.
I think I was
Yes.
talking later more. It's like, yeah.
Good.
Yeah.
But let's look also at the results of post-training quantization in NNCF in case of one of the state-of-the-art models for Auger detection, and YOLO V8. In this case, when we quantize the model from floating point 32 to int8, and now we are talking about post-training quantization, so the model is fully quantized with the operations. So it's not only weight compression like it was before for the large language model. The change is about 0.017, right? So it's not a big deal, I would say. We still, I think, can afford that accuracy drop here. So yeah, this model is not very sensitive for post-training quantization. Some of them, some of the models are, but in this case, it's like a, let's say, almost free lunch. So we quantize that model, we have much better, faster performance, and not much of accuracy drop. So if we look at the another image, the comparison between floating point 32 and int8, we can see that there are differences in scores of the boxes, right? But still, the same number of ducks are detected. So the original model missed that duck, and the quantized model also did that, right? But other ducks are still detected well. There is also something like hybrid post-training quantization. It means that we quantize only some of the models. In case of LCM, we have three models: text encoder, VAE decoder, and UNet. In this case, UNet is quantized both the weights and activations, and in case of text encoder and VAE decoder, quantization is only applied on the weights. So we can see the comparison on the picture on the right. So when we run the floating point 32 model, it works good, right? But when we do the int8 post-training quantization, just that, we see that the performance is not good, as the quality of the model is not good as it was before, right? So this model is, let's say, quite sensitive to quantization. So that's why we use int8 hybrid post-training quantization to preserve the quality of that model and to have some better performance with quantization, right? And there is one more thing I would like to show you here. The performance comparison. In case of OpenPOS, this is these two videos, GIFs, are running the same model, the same video, and the only difference we can see here is performance, right? This one on the left is running floating point 32, so we have about 40 frames per second, and if we quantize that model to int8, it's a post-training quantization in this case, it will give us about 88 to 90 frames per second, 2 times faster, and I cannot see any difference in accuracy, right? It's still very accurate. And what's more, 16 megabytes versus 4 megabytes. Not big deal in this case of model, right? But we already looked at large language models, 10 gigabytes versus 2.5. It makes the difference, right? If you would like to look at the code of the quantization, we have pure codes for that here, for post-training quantization, accuracy control quantization, and quantization hour training. And
These are sample code you can run.
yeah, these are notebooks in our OpenVINO notebooks repository. Everything is open source. Feel free to download and run.
Some people use it to teach at university, I remember. So feel free to download this. It costs us a lot of money to make them. It's a lot of engineering time to put into working mode.
Yeah,
Yeah.
I can see that some people still taking photos, so I will pause
But I think
1-2 seconds.
yeah, there's a lot of detail. We're gonna show a couple demo why this matters, especially I'm holding a laptop, right? You have a big server farm, you have a lot of money with RAM and everything. It's okay sometimes for your work tasks. But today I'm gonna show you a chatbot. Anyone heard about Llama 3? Do you think I can get it running on this laptop? I'll show you.
Yeah.
Stay tuned.
And I think this is the last slide, exactly what I would like to show you today. So more on quantization and using NNCF OpenVINO will be covered by Alex in the last part of this tutorial, starting at 3:30. So we need to change the time here. So please come here and listen to that part. And now it's time for Raymond.
I gotta talk about a lot of things today. But before I do that, let's do a quick demo. It's okay. Help me. Wait, Adrian. How do I plug this in? Can I plug this in for a second? So, yeah, this is your machine, right? Yeah, let's plug it in. You have enough space? No. Maybe that one, otherwise it will be. Yep. Put it on the table then. I'll put it on top of your laptop, it's fine. Yeah. All right, this. I need to connect. Yep. No, I have to like that. It's okay. All right, so now we know laptops are stackable. Yep. So we talk a lot about why we're here because I need to use the mic, so I gotta try to stand here, but I'm not that tall, so I don't know how I can get taller. All right. Damn it. Oh, wait, let me get it right before you take a photo of me. Again, welcome everyone. So this part of the talk, I gotta talk about the hardware a little bit. I may bore you to death because it's hardware. It's very hard to explain all of the concept in short amount of time. But I think it's important to explain why this matters to you, especially your developer, you're in computer vision, your researcher. Is think about machines that's available with people today. Do you know how many laptops we ship every year? Anyone want to guess? You can look at our financial report, by the way. Sometimes goes up, sometimes goes down, okay? But we talk about in millions. So if you think about cell phone, laptops, these portable devices that people have, the only way, I'll say the only way, because I try everything almost, to make things run is really to optimize and compress. So today I gotta talk about one of the very recent effort we put together is called Lemma Free. So we can actually have it running locally on a laptop. To no further ado, first question is people know what Lemma Free is, right? Okay, you're in a good place then. So I'm gonna show you like what is CVPR, let's say. What you can do locally today. Of course, always zoom in, but let's say, hold on. I have no white background yet. Okay, display settings. I'm so used to dark mode, guys. Anyone? Appearance, dark mode. Okay, let's light mode. Oh, hurt my eye. Oh, my eye. We're engineers, right? It hurt our eye. Thank you. Well, step one is like, this model is about 8 billion parameters, right? I want to tell you a story. The story of like how this actually doesn't work. Then we come to the working part. So about a year ago, remember, we have Lemma 2. So at Intel, we're trying to say, what can we do to make it run? Because when we came to us in the beginning, it was very interesting. We have 7 billion, 70 billion. Remember anyone of that? Yeah. And trying to run it. Anyone test it anytime before? Anyone? It doesn't work for many good reasons. The number one problem I think we dealt with at that time were memory. So in the old days, right? Say old days, just like 10 years ago, a lot of computer vision tasks were compute bound. What it means is you have a fast machine with some good amount of like CPU power, GPU power. You can crunch it through. It may be slow. But today, when we talk about this large language model, it just doesn't run at all because you don't have the capacity to fit it in, right? So why this is important is, let's look at this number. I'm very thankful that we have shared memory because if you have a graphics card with 16 gig of dedicated memory, you know how much we have to pull to get it there? So it's a very expensive task, right? To get that dedicated memory. And today, when we're running this task, as you saw, we're running what is CVPR. It generates this test all locally with no internet. Again, this is local. And the number one task we're trying to solve at that time was to fit it into the memory. So it was a very fun story because at that time, our CEO said, let's get it running. For real. It was like I was on stage with Pat, our CEO. And then the first thing I say, it doesn't run because we don't have enough RAM. Right? And then the whole team came together. It's like, what does it take to get there? The number one task we thought was like the compression algorithm is not just in 8.
because if I look at this, you multiply a little bit, it actually still blew up the 16 gig of RAM, right? That shared memory, we only have that up to 16, I'll say, but you need some headroom. So that actually came to that whole journey of us, especially the team here, spent a lot of time to compress the model. And of course, with this kind of compression, it comes with a couple of advantages. One is once you actually reduce the model, the memory footprint, it actually saves a lot of headaches. And the other thing is, once you actually have the compression ready, it helped two things as well is it helped the deployment because actually I can give you this file in 2 gig. Anyone want to get a copy of this? You can come and get SD card and then plug it in, you can get a copy very quickly. And this is very important to all our use cases that I want to talk about today is hardware optimization. And then anyone want to try ask hard questions? This is like a chatbot, right? Anyone come up with one question? Break the lemma 3. No one wanted there? All right. I will ask a hard question. What is a free body problem? Because I see a lot of you may have watched that Netflix show. And how to solve it. Anyone how to solve it? Anyone know a free body problem? No one watched Netflix anymore? You read the book, okay. It's pretty famous, okay. It's in physics and astronomy that I think it's a long time ago. It's talk about like we have stars, you have planets, and then you have all this like different things like they're rotating, right? And how do you know the motion? And it's really cool. I have actually running this locally, and this model actually trained the whole internet and trying to, you know, basically from this 8 gig of little RAM and talking to me. Isn't that a bit freaky? Yes, because you're trying to read out. Why is it challenging? Solving the free body problem is difficult because the equation of motion involve complex algebraic expressions, integrals, And these are all generative. And I think for me, for many years in the industry, I think this is very innovative to like use cases wise, because I will never need to go to get a burger talking to people one day, very likely. Because when you think about self-ordering, this actually can serve those purposes very well. Et cetera, et cetera. But I hope this is a good starting demo to inspire you, because in the next set of laptop you'll get, very likely you'll get some functionality that comes with some generative AI. And they better be open source, guys. Come on, we are the research community, right? All right, that's the beginning of this again. I will go back to the optimization. Any questions? Anyone want to run this? I have a copy. You want to try it? Okay, here's the trick, okay? You go here. Yes? Sorry? Yeah, it does. It's the fun part. I actually tested. So very good questions. It does work on the ARM processor as well. However, support is limited, okay? So I cannot promise it will work every day, because like we still based on the open source community to update some of the work. But our engineer, including myself, I was the first one tested. Yep, I have a Mac in my backpack. So yeah. All right. But to learn this, type this, and then you go here. This is our lovely website where we have all the content. And here, our team here, where is it? Where is the type of content? Oh, the index file right here. No, not the index. What's it called? Sorry? Yeah, this one. That's right. So here you can look for, what do I look for? Lemma or large language or LLMs? Yep, look, all demos. I love the interface. And you can build an agent now. Oh, I didn't even know that. When did that happen? That's brand new. All right. I'm pretty sure I'm using this one. This is the one that we talked about today, right? Yep. And you can see all the documentation here later. But more importantly, you will get access to the actual source code. And after the optimization talk, I'll explain how the source code work a little bit, how we actually compress, load the model, and get it running. Again, I would love to give people a break, but sorry, no break here. If you need the bathroom, just run and come back. Don't run out of time. But definitely, this is something really worth trying, because if you do it, all your friends will be jealous. Trust me. Okay, my friends are very jealous when I get this running. So let's give it a try. All right, let's get back to this hardware. So no one actually watched Netflix and pre-bought the problem. Come on, like you did, right? It was good, right? Good, right? It's good stuff. Oh my God, this audience is hard to impress. All right, let's get started. All right, so where's the mouse thing? Right here. Let me try it, okay? Let's see. Doesn't work. Nope. Nope. Yep. Okay. All right. God, you give me the hard slides to explain. So this could be boring. I'll try really hard to make it fun and exciting because it's hard work. It's hard. So let's talk about why some of these learning funnel down to this open source community and how like our hardware been I'll say we not sometimes have the fastest machine, but sometimes we talk about scales, right? You think about, let's say, Xeon server. Like the first question I joined Intel was like, why do I need a Xeon server? It runs on my laptop, right? But when you come to deployment, it starts to matter because when you're hosting and you start to look at first different things, right? One thing we actually briefly talk about, and I think it's important to discuss here, is some of the collaboration Intel have done with other companies, right? So this is actually Google. Google came up with that idea of using BF16. It's a very important thing back then. If anyone read the paper, it was about, okay, we're not very good at processing all this training because back in old days, right? Okay, not that old ago. When they start looking at this problem, they want to find every way to squeeze the performance because let's say you get 2x faster. The training time talking about 2 weeks to 1 week. It's a huge problem, guys. Like, and think about like, oh, it takes 10 years to train this. You're not gonna be here, guys, anymore. We're talking about 10 years. So when I before Intel, I was actually working on CUDA, by the way, just full disclosure. I was an NVIDIA guy. Then I do Intel guy. You know, I love hardware by heart because I think at that time when you see acceleration, you can open a lot of possibility. And this is actually a very good collaboration at that time because based on the study, they figure out, whoops, last slide. This actually, you have no loss in your position at the end, right? When you finish the training, close to, again, I know you're looking at me, I know, I'm not over promise, but the trade-off is huge, because at that time, always think this way, I'm here talking to researcher, right? But I'm in industry, I always say hardware is always later, so a bit slower, than the research, right? You always like use something a little bit older than you expected. And that took us like many years to implement, but today become a gold standard. So I always almost thank all this community here that actually push us to do the hard thing, right? So a lot of these ideas came from the community where they're trying to solve really hard problems. And why that's important is one of the instruction set that why we care about quantization is under the hood, VNNI looks like a pipeline, right? When I think about instruction set, the better way to explain this to you is think about how we multiply something first, okay? Anyone have an electrical engineering degree here? No? Okay, one? All right. Hope you don't need one to understand this diagram. Let's say you're trying to do something very simple. You're multiplying an array, right? This is a dot product, for example. You want to do every time you do something like this, in a computer, right? You can think about, okay, you're just taking all this little digit and then you just do all this extra like step by step to get to that point, right? It's like a little pipeline. What we have done is at Intel, oftentimes we will notice this kind of operation, especially when we think about convolutional network, some of the operators actually happens quite frequently, right? Like optimization 101. What do you optimize? Optimize things that people use. The greedy part, right? What's the part that often being used a lot? So when we think of VNNI, it's really a combination of these fusing all these instructors into one clock, right? Basically, in a clock, you can actually get it all together and multiply. And why that's important to you is whenever I tell this audience today is whenever we think about optimizations, you don't just think about, oh, just converting some number. We actually look all the way down to the instruction level. And that's something actually, if you're very interested in, talk to Intel, talk to us, and see if there's any particular use case that you can come up with. Because that actually branches it down to, okay, Remember how I say it's important that we know how to multiply. When we start to think about there's more matrix multiplications happening. And the best way to think about this is like one of those AND operator that use a lot, right? When you do matrix multiplications like that, we also put in a hardware layer where you can do this directly, right? To you as a developer, I gotta give you good news. You don't have to read this. It was instruction code that you have to read. We have something called a 1DNN. So that actually is one of the library that we came together. So then you don't have to deal with this instruction set as much as you can. And also we work quite a bit with the community. If you're using your data scientist, Panda, sometimes if you look at the instruction set, we support there from Intel, there's an extension package we provide. So there's a lot of extension package we provide to get this performance out. So why I'm skipping through this, because this is the part that gave me a lot of headache back in the old days. Anyone tried to use GPU? No, right? I still want to give you guys an insight into why you should consider using the GPU. I'm gonna skip this one little bit, but this is like a sales pitch to you is I had so much hard time to getting my driver set up at one point. And this is like a slide we put in to help you. If you today trying to get GPU installed and set up on your Linux driver, you're good to go. All right, we simplified that process, and that I love that team making it happen. And why is that important to you is once you have this GPU driver, the rest is history, because now these instruction sets, this is so I talk about VNNI for Xeon. We talk about AMX a little bit, which is those instruction set for accelerating. So you can always anticipate we have more extensions. So I think there's like a little bit of the community fighting as how many extensions I need to get something done, right? Like AMX and then all this. This one is actually more interesting because I was talking to the GPU driver team at that point. Anyone from Intel from the GPU side? I don't think so. From GPU, no. Anyone from Intel knows the GPU team? Nope. It's very fascinating how they architect the GPU to get acceleration off. And one thing is the capability of having this systolic array pipeline. Anyone know what that is? All right, Alex, explain this one. You know this? Yep. Hope. Yep. Right. So, and that person there keep raising hand too. Yep. So what's your background, by the way? It's quite intriguing. Yeah. Self-driving cars? What's the biggest problem you deal with all the time as a self-driving car person? I think you deal with a lot of these optimization headaches. Ah. Okay. Yep. This is why I love this audience. I'm just like looking at them. Yeah. Good. All right. Again, as a developer, what this means to us, right? Like you're perfect, right? You're my perfect audience, right? But for the rest of the people, what does it mean is when we come up with these architecture, especially you want to think about these are the fundamental blocks that help you to boost your performance, right? If you have benefits, right? Why you want to choose a piece of hardware at one point is these are fundamental building blocks allow you to accelerate. And that's great because again, if you're a developer, you care, is it like the CPU on a Pi sometimes we do prototyping? Look it up. Look at the Curie and then see if you have this acceleration. And this actually is a very critical one if you want to get very good throughput from this. And that is a laser there? Come on, where's the laser pointer? This thing have no laser pointer? All right, that's fine. So why I'm telling you this story today, I think more importantly is software and hardware should be side by side, right? This is not the audience for hardware, but most of the time people only think about like, okay, to get into this field, we have to train our model, right? We need to start from scratch. We need to like be doing this and getting a lot of that. But I think for me, especially in the last 10 years in research, now I'm in Intel, what I'm learning is you need a deep understanding of the entire pipe if you really care about what you're building. I think it's Apple saying that if you care about your software, build your hardware. Right? If you care about your hardware, you should build some software. So this bidirectional things is something that I really appreciate some of the engineering team I work with at Intel. Again, thank you engineering team at Intel because you did most of the work, right? All the hard work to get this together. Then for you, the learning I think for AI deployment, again, I did a quick survey. I assume a lot of you haven't really deployed things in the millions, right? Like to a very big audience. We always think about cloud, edge, and then the client use case, right? To be almost funny, like at Intel, we have different groups handling different of this, right? We always think about trade, right? If you care about deployment today, the first question you ask yourself is, where you want to put the data, right? How do you want to host it? And I have an interesting conversation with some customer, for example. I'm not gonna disclose the name, of course. I'm not gonna be, gone. But a lot of customer see the next generation of compute can happen on the edge again, right? What does it mean? Does anyone know what an edge in cloud means? Like, it's a very industrial kind of fluffy word. Yes. Anyone else? I'll explain a little bit, if not. Cloud is like, okay, you already may have seen the centralized approach with, again, like the prime example is always Amazon, all the server farm, right? There's like big data center, right? And the edge is like whoever running there that's supporting some of the system. Like, I don't call this an edge machine usually. Like sometimes the smart camera. Think about actually one use case is anyone from China here? Any Chinese? Yep, China. A lot of the camera system cannot be centralized and compute directly, right? They have to have like an edge platform where support some of the smartness. Actually, I did a hackathon. One of the very good hackathon was in Taiwan, and I want to share this to you all because, to be very like, cost effective, you have to think about where the compute happen because the cost difference is huge. One of the example they do were they trying to prevent robbery because like at one point there's always people walking with a gun, with a knife, with some sort of weapons. It was scary, and then the response time for the police was very long because the time they have to get the call, they talk about, let's say, in a minute, right? It actually can be a life-threatening scenario. So do you expect to centralize that and process that information, and hopefully the network doesn't go down on the moment, or you want to process it on the edge, right? So then there's a lot of those momentum where people want to have certain compute that happen on the edge to make quick decisions, like try passing, right? You don't want people to go to into garage, right? You want what happens is like upload to the server and come back. Sometimes latency matters. So I find this is quite intriguing because if you really want to think about deployment, the number one is figure out how to put the compute, where to put compute, especially if you get a perfect idea of, let's say, self-driving car. You want to connect it to 5G before you start driving, right? It doesn't happen that way. It has to be really well thought out. And if I read this through, again, cloud is very defined by the centralized one, and then edge is what I see is you want to have a much more real-timeness on it. And to us as well, I showed the Lemon 3 demo. I think that was a prime example. A lot of people would love to have your laptop ask. Actually, it's a fun thing because our company banned Gen AI in the beginning as well. Like everyone banned Gen AI, I remember at one point. Because like when you're talking to it, they actually take your data and retrain it, right? I think you heard that news, right? And then we as Intel as well, it's so easy to leak company secret when you talk to a generative AI algorithm that you don't know. You have no control. So that actually is a very important thing that also we trying to help prove here. And again, a little bit of marketing here, bear with me, okay? AI PC doesn't mean much to me when I started, but today is a new category of compute. What does it mean to you, right? Again, the reason here I'm from the industry, I want to give you like some of the marketing direction that the whole industry is doing, is where the consumer like you today. I can put a $100 here bet on the next 3 generation of laptops, every single computer we'll have some sort of NPU and GPU accelerator, and then all the optimization tool that you saw to accelerate all the workload we talk about, right? Most likely your paper that you run right now on a server farm, if you spend enough time, figure it out, it can run on a consumer electronics like a laptop. And that's what some of the very big momentum is happening. We categorize it as an AI PC. To me, it's a PC that actually have a lot more optimization for AI use cases. That's what it means. To me, this is a great opportunity for especially if you care about open source community, because now, how many times you give some source code to your friend and then they say that I cannot run it? You face it once in your life, minimally once, right? How likely you can get something running on others' machine is very difficult. So this category of work actually to me is a powerful one, and for consumer and for enterprise, it's a very big change in terms of how we see compute, because people are going, like some people actually say, hey, I cannot pay for this anymore. It's too expensive. How about I just get a lot of these kind of individual device and offload the compute? And that brings to this topic, to the architecture of this, how we started. Interestingly, we the first one talk about this. I feel good and bad because we actually make the whole industry talk about AI PC. If you hear AI PC, our boss started it. I was behind the scene before the keynotes to give the Llama 2 demo. That was a demo number 3 now on that. Because we believe heterogeneous architecture moving forward is, I think we are one of the first one to integrate NPU to a lot of our hardware in the old days. NPU is not new, by the way. It was a long time ago. We have something called the Movidius chips, MirrorX. So I don't know, maybe we didn't talk about enough. We do have some of those little neural compute stick that actually runs on Raspberry Pi. So I actually been giving that out 3 years ago. If you're a CVPR 3 years ago, I gave them a free neural stick most likely. So we've been doing the NPU for many, many years. But I think the high throughput of the GPU now also very important. But this is the balancing act. If you want to remember today why we're doing this kind of like a very kind of weird architecture, or weird because we have so many different processing unit, is they are becomes semi-optimal for different tasks. Because when you get a laptop, of course, you use GPU maybe for a little gaming media use case. But today we actually use it as a power horse for a lot of AI accelerated tasks, like for example, the Gen AI work. But the NPU becomes extremely power efficient. I did a demo that show you that we can cut the power by half running the same workload, approximately half. Again, hold me to it. I will show you some number. And then the next generation. Anyone know what's the next generation look like? Today I'm talking about this generation. Do you know what's new? Anyone heard the news yet? No? Okay. This is called Meteor Lake, right? This is the today's generation Intel Core Ultra. The next generation, I think 2 weeks ago, our boss was on stage at Computex. So we anticipate a huge performance boost, 2 to 3x easily. And look at the die size, it's like this much bigger. So what is happening is a lot of momentum and effort like putting behind each of these processor. The GPU get faster, NPU definitely a lot faster. They talk about over 40 TOPS. Anyone know what TOP is? You know, TOPS? Okay, nodding. You know, yes, TOPS. Trillion operation per seconds. And what does it mean? I don't know sometimes, depending on your workload, right? But to me, is as a way to, you know, like guessing how many times I can trigger something, operations, right? But that we get 4 times more. So I think it's 4 times the size of the die. And then we even re-architect it. So the NPU becomes very powerful in the next generation. And even the GPU is a new one. What is it called? Battle something. Battle Mirage, was it? Battle Match? Battle Mage, yeah. So I'm so excited about this, guys. I'm like a blue team guys, you know. Anyway, so think about these is like what's inside of it. And when I think about the new processor, it was really cool. Because when I talked to the CEO, how he explained it, we were like making pizza. Intel is making new type of like processing unit, like we stacking different, it's a tile structure, right? We literally stacking different manufactured chips, right? I think the last one, the one that we have, they are mixing like the 3 nanometer, 5 nanometers, different manufacturers to put this together. And this is actually very cool because if you have the idea of the next generation of compute, let's say you have some really crazy idea, I don't know what that is. If I know it's not crazy enough, and you want to integrate it into the silicon, it's possible. But make sure you fundraise a lot, okay? So capital involved. But the whole structure allow you to literally like make like a different toppings, you know. Anyone got a mozzarella cheese, you know, pepperoni, and you can literally glue it together, and then we make the bottom of it for you, which is the rest of that packaging, which is a very difficult thing to do. And that to me, or to us in general, is we will see this kind of very interesting up curve where Media Lake is there, but you know, right there we have all this. Definitely in the coming up weeks or months, actually, keep an eye on the Lunar Lake, and then this will give you some insight into what else we can do as well. So for CPU, there's a huge change in architecture. I don't think we discuss a lot in the community. This was kind of like I think it was like ARM started it, kind of like the big little, you know, kind of thing. And we have that because this actually where it put a lot of power efficiency without P and E core. But to me, like if you are a developer, if you understand your workload, you can actually now because like we have something called a thread director. It's not the best thing ever. It's not the worst things ever. For me, it took me a while to figure out how to use it. But it's an OS level where now you can put the workload however you like. And that's very powerful because you have your phone, right? Why would it run so long? You really think it was running everything at the performance core? No. So this actually give you that alternative when you come to doing compute. And that's something worth thinking about when it comes to CPU architecture. And I talked about VNN already a little bit. So this for the DL boost, you can see it in almost most of the new processor we're coming today. So that's anything that not a promise, but you can keep an eye on. So if I gotta remember how to get good performance from Intel, look for Innate, look for AMX, look for XMX, look for these extensions, and look for MPU. Actually, the next generation one is like awesome, right? And also look for the memory. Actually, make sure you get enough memory. If you want to build Gen AI stuff, make sure you get at least 32 gig of RAM. Okay. Anything less than that, no promise. Because because the RAM share with the graphics card, so it matters a lot actually. And yep, that summarizes some of that, like what I think is very important to you all to think about. This architecture to you is really to get that, okay, what will give the best performance out from the community. And let's see, this slide, I remember this one was about DP4. Yep, this is for the graphics card as well. So that's an acceleration capability. All right, so let's slow down a little bit. Let's talk about the NPU. Anyone ever try on NPU? No, I don't think anyone here tried it yet. No, very, very new to most of you, right? So I think the best way to you right now to think about this is I'll think about the software level, because if this is a hardware talk, I would talk differently. I'm trying to make it so that everyone can think about this. When we think about you build a silicon, right? The problem is you want to serve purposes. Graphics card is not designed for AI by definition. You know, when it started, it's designed for rendering, right? It's designed for what kind of rendering? Think about, right? Graphics, right? So a lot of time when you think about architecture, I always think about what are the fundamental building blocks to get the most out from it. The step one, I think, for us to think about is how can we, like as a developer, be able to utilize this as if like a CPU, right? That's one of the mission that we've been thinking about a lot is, I don't gonna overpromise you, but ideally, when I work with the engineering team, is you can use the NPU just like how if you write source code for the CPU. And fundamentally, the underlying architecture you don't have to worry too much. And that's one of the promise, like when we work with the clients group, because it should be, I don't know, I should mention, but if you look at your phone, they do have the neural engine, like most of them. Yep. And no one talk about it because it just works. Because when we write APIs, we can wrap around and give it accelerators. But I think these are some of the advantage you should remember is it's redesigned for low power and AI compute. So this is a very good momentum that we'll see. And it's designed for they're all programmable. So OpenFino, the reason we explained this today is to give you the little of that programming kind of product, so you don't have to like go from the instruction set level. You can try to compile from scratch. It is open source and it's on Linux. So if you're a really crazy hacker like me back then, I actually port drivers for Microsoft Kinect, for example, to run on Android. You can definitely do that as well. You can take a look at the drivers. And this actually natively support IN8 and FP16, and then don't do FP32 if you don't have to, depending on your positions. So I ran a couple demos already. So any questions? Audience, questions? Anyone have any ideas what to do with this MPU now? You have some idea? Let me know. This could be yours and to bring home. We do have an after party. Anyone know that we have the after party? No? When's our party? Shoot. Adrian. First day. Okay. So we have demo with food, but more like I know someone like turning head party, right? Yes. At the end, yeah, we'll go to the end of slide. Make sure you stay for the slide. VIP invite only. So if you're in this group, I guarantee you can get in. Okay, I think so. Hope so. We should. Can we guarantee that? Yeah. Okay. Talk to him if anything. Okay. I'm just the manager, but I shouldn't be saying this. Okay. You should be able to get in. Okay. Depending on the line. Okay. But that after party is where we'll bring some engineering. You can just sit down and talk, have a beer with us, a wine, whiskey. But more importantly, we have community members from OpenCV. OpenCV is actually still, around and doing a lot of fun things. And then they will be there to show you demo as well of some of the activity we have done in the community. Any more demos we want to show? MPU, yes, let's do MPU demo. You know, do it. You guys want to see the MPU in action? We have one. So yeah, we showed you already OpenVINO basics. We can also show you, we also showed you latency consistency model. And then we can show you a live object detection running with OpenVINO. So we will start with CPU. Let me just change one line of code then. Yeah, it's CPU, good. So let's start. Again, the purpose is to show you can write code in the CPU like the same way. And then MPU just happen in the background, but we have to compile everything from scratch. So it's running CPU right now. We have about 1000 FPS. What's important also, so I can show you the power usage of that inference right now. Yeah, I know. I just need to open that. One moment. So we can see also power consumption of this laptop right now running CPU inference. It's about 40 watts, right? So it's quite okay, let's say. But let's see if what power consumption we will have and what performance we will have when I switch the device to something else like GPU and NPU. So let's start. We started with CPU about 800, 900, 1000, and then I'm switching the device. I mean, it's not exactly FPS, it's latency per inference. Yes, yes. I think the FPS is a little bit misleading. I don't have that 1,000 of frames coming to my machine. And right now, you can see that also in the idle states, we used about 12 maybe watts or something like that. In case of GPU, we have more than 1,100, 1,700, 800 FPS. And at the same time, our power consumption is lower. Almost half. Yes, about 20. Oh, thank you. It's exactly half. So they overpromised that part. But I think this important part to a business perspective for enterprise use case is making a Zoom call. So anyone did a Zoom call recently after COVID? Yes. You know how they blur the background? That's exactly why they want to buy this NPU. Is when you're blurring the background, you're burning up your battery.
Not this one.
And today, if you do the background blur with the AI PC, it does actually utilizing the NPU for you. And there's a demo, I think, at the top bottom if you show it.
Yeah, I'm also switched to NPU right now, so we are running NPU 300 FPS,
Yep.
400, 700,
Cool.
it varies a lot. And the
Mhm.
power consumption is even lower, right?
Yep.
17, 18, 19 watts. So it should be something like that. So the power consumption is the lowest one from these devices. At the same time, the performance
Adequate.
is worse than GPU, right? But still,
Adequate.
who needs 600 FPS, right? If you run something in the background, let's say like background
background
blurring
blur.
or object detection or anything like that. So this is what I want
So
to show you.
This is the part where I find it fascinating because when we partner with Microsoft, we have a couple partnerships. Zoom, for example, is our partner. We see the use of these hardware technology. Again, our job at Intel, we don't build software a lot. To be very frank, like we don't ship software like, we're not the App Store person. We don't build very fancy applications, to be honest, because that's not our role. Our role is to support the community to build this. So when we see Microsoft and Zoom and others utilizing some of the NPU work, which happen, again, you don't know that it happens because, oops, sorry, I gotta click here. If you look at the Microsoft, oh, I didn't say it, where it's okay. When we start to think about meetings later, hope you remember me later when you have your next Zoom meeting on the laptop. Why you get 4 hours of battery life or 8 hours, but not one? It happens before. It's because of these extra effort we put in. Even you like doing Zoom video call or Maxo, it's still a lot lower power than before. I think that's a very important thing, power efficiency. And that's something worth thinking about when you're developing your applications and think about the audience. And that's a lot of big lessons we learned. Do I have to do the next one? I forgot, the model surfing. Is it yours? Is it yours? Is it mine? Okay. All right. Now let's complete the story. I'm not gonna say OpenVINO again. If I keep saying it, I gotta take a vodka shot. Model surfing. I don't want to oversell this, but these are lessons. I think the most important is these are the lessons we learn is every single thing that can go wrong, we have to face it once, to be honest, right? Like look at like surfing a model. In this case, what model surfing means to you is when you have a system where you have multiple clients, right? To use the system. It can be, again, I talk about surveillance camera system that you want to make sure there's no one like stealing the food from the checkout. By the way, that's $1 billion loss problem. Anyone know that? Anyone know behind the scene how many? Like, let's do the math. Let's think about one of the biggest supermarket today. I cannot say names, can I? I don't know anymore. Think about them. Let's say they lost $50 per store and multiply every day across the whole year. How much are they losing? Just $50 per store. Every single supermarket in the world. It's a lot of money, right? That come into our attention because very likely you parking your car today, they read your license plate, it's Intel. And we have to serve the model. We want to make sure that you don't want to, let's say, have too many computers just to set up to run, let's say, some of the workload. So surfing is one thing we notice is like, okay, want to have some algorithm running on the edge. Maybe you have 4 camera system or 6 camera, wherever, and you have one machine to run it. You can do things like that. That's one thing we support. And that is also very important is you can predict banana if you're in the, just kidding. If you're in, let's say, in the store, and you can also serve different purposes. Let's say in the checkout experience, which happens a lot actually. If anyone could go ever shopping and look at a checkout system, you look up and look down, most likely it's running some sort of this, right? And then all this workload, we also supported it. And that's important because you don't want to deal with it. This is actually really painful to deal with if you don't know what you're doing. And you may ask, how does it compare to torch, torch surfing and all that. We also support that. So if you're using PyTorch today, in this new release, we officially also come together with that. So how does it look like? Let's say today you have a demo, you want to run the, let's say it's this is a, hold on one more time. This is the Llama, is it Llama? Large language model text generation. And you want to run that. And what you need to do is very simple. Anyone use Docker? I assume you do. Dockers? Yep. So behind the scenes, very similar. You basically have that Docker as the backend where a lot of well, basically you package everything into that. I think that's the only way to run anything anymore nowadays, because back in old days you can like good luck with your own script. But that's like the, for example, in this way, with this now you have this backend where you're running this, and then now you can just like have client just making a request to the system. In this case, what's the theory of relativity? I'm on a free body problem. Keep going. Sorry, guys. I need to keep my theme together. So, and then you can see all this can happen, and you can serve many customer. Remember, I showed the chatbot. You can also serve that for your family. I don't know, guys. From a use case, I don't know. Maybe for your children to learn. I don't know. But this is very important to all of us. Is once you understand how this run, and you have the client call, very, very simple to scale. And that's something I would love you to, I'll challenge you when you're next time, when you're trying to deploy something to people, when you build a demo, let's say, please try this and then see if it helps you in your workload. Okay. Do I have to go through the whole thing, or is this yours? Is this yours? Is this yours? All right. Again, I talk enough. I hope you learned something from me today. My job at Intel, again, I'm the evangelist. I'm also the manager, and so I'm really proud of my team. So again, thank you for the team coming today, and I'll have Joel to come and talk about the rest of this. And to introduce Joel, say hi. She's a professor, by the way. Yeah. Oh, by the way, I got my PhD too, just a long time ago. All right. All right. Yours. All right. We talk about extension. Oh, class, thank you.
Okay. Thank you, Raymond. Thank you, everyone. Well, next part is the introduction of OpenVINO training extensions, which we call it OTX. Of course, I will introduce very briefly here because Summit, our expert on OTX, will have our first module next to teach you how to use OTX for model training. So I'm gonna go through this part very quickly. So I think everyone remembers that from end to end for AI-based solution, we will have all those steps involved, from data set to from data collection to form a data set, and finally to build and to train your model, to optimize and to deploy your models. And of course, training is very important. And here we would like to summarize that for OTX, it is our one-stop shop of verified algorithms for many vision-based tasks and learning methods. And also we provide both ways to perform OTX training functions like simple CLI and also Python API for you to start very quickly. And also our OpenVINO function has been integrated within OTX to perform optimization, inference, acceleration, and deployment for the final trained models. Okay, here are very simple code snippets to start using OTX. You can also, you can either choose CLI and also choose Python API to use OTX. So the code here shows you it is only one simple line to start your OTX journey. And also here, as you can see, OTX provides you features like for the task types, like classification, detection, and segmentation. Those commonly used task types are supported by OTX. And also for learning methods, It is also supported with fully supervised, semi-supervised, for example. And for the functionality, we also provide, as just mentioned, both Python API and CLI. And here is a simple example of how to install OTX. Okay, so as mentioned, Summit will give you a very detailed introduction on the OTX, so I will skip this part. But next part is our introduction on OpenVINO notebooks. I think just now Raymond has direct you to the page of our OpenVINO notebooks on GitHub repository. So this is totally open source free repository to teach you actually how to use OpenVINO to convert your models, to optimize your models, and deploy your models on different hardware devices. It could be CPU, GPU, or NPU. So if you swipe this QR code, you can also direct you to our OpenVINO notebooks GitHub repository. And next, I would like to show you a few among the more than 150 notebooks we have provided in OpenVINO notebooks. I would like to introduce a few of the examples, notebook examples we have provided within this repository. So as you just, I think you have seen our live demo of object detection just now. And also we have provided example notebooks like pose estimation. And this one, I think some of you also may have tried it, segment anything. And this one will give you a very good depth estimation map. And for YOLO, okay, for the family of YOLO models, we also have several notebooks to show you from YOLO 5, I think, to YOLO V8, YOLO V9, V10. We have all those notebooks to show you how to use different YOLO family models in OpenVINO. And of course, for Gen AI, we have provided notebooks for Gen AI for vision models. Of course, starting from Stable Diffusion, we also have LCM, as Adrian had shown you with just a live demo. And remember that from 1:30 today, this afternoon, I will also teach you how to enable LoRa for customized LCM models using OpenVINO in our module 2. And besides that, we of course also have ControlNet to control the generated image in different styles. And with that also we have Pix2Pix. And this one also I think is very interesting. Anyone have a mobile phone can swipe those two figures. It actually are two QR codes generated with the model QR code monster. So I think using this one, if you want to share your link, it can replace the ordinary black and white QR code image. Of course, beside the text to image models, we also support text to video models. And here we are using Zero Scope, optimizing it with OpenVINO and deploy it to generate this short video showing a panda eating bamboo on the rock. And so you can also try this one to generate a short video on your own device. And besides that, we also have Film Slow-Mo to generate the interpolation frames and finally to help you to generate a short video, a film. Okay, and besides that, we also have multimodal models like Lava. You can just send into an image and ask questions about this image. And also Llama 3, as just Raymond showed you. And besides all those ones, we also have the music generation models supported notebooks and text to speech, speech to text. All those different kind of models have been supported and also optimized in OpenVINO. So you can choose whatever you want to play with within our OpenVINO notebooks. And for those who are using C and C++, we also provide you another repo we called OpenVINO Gen AI. It includes the Gen AI pipeline, some examples in C and C++. So in this new repo, actually, we provide those tools and examples. For example, we showed you how to use a benchmark tool for benchmark the performance of large language models. So using this one, you can evaluate the first token latency, second token latency, something like that, and the memory footprint you will use during inferencing these large language models. And of course, we have C++ samples of text generation and also stable diffusion LCM with LoRa. And speaking of the OpenVINO ecosystem adoption, I think the numbers we listed here in this deck has already been surpassed. I remember, a few days ago, I saw the message that we have surpassed 5 million downloads, right? 5 million downloads for installation of OpenVINO. So, 5 million. And so we also want to call out to our developers here. You can also contribute to our OpenVINO toolkit. It's an open source project. So we have the good first issues here in our OpenVINO toolkit repository. And we listed some of the challenges for OpenVINO toolkit we haven't solved yet. But as an open source project, we encourage developers to provide their solutions to fix these issues for us. And you can submit your solution through PR, and by reviewing by our developers, by our engineering team, you can finally have the opportunity to merge your solution within our OpenVINO toolkit and have more than 5 million developers all over the world using your solution. And I think also, as just mentioned, we have OpenVINO within the Google Summer of Code. I think this year we have the third year in a row to be accepted by Google Summer of Code as an organization to have projects contributed to Google Summer of Code accepted. And I think starting from 2022, we start from 3 projects being accepted by Google. And after that, we nearly doubled the projects to be accepted each year. So last year we have 5, and this year we have 11 projects accepted. So we welcome our contributors, developers, to apply for our Google Summer of Code projects and to be part of this challenging but interesting projects. Okay, this is one of the projects to be implemented by this year's Google Summer of Code. Okay, we are near the end of this fundamentals part of our tutorial, first tutorial. And so by swiping this QR code, you can reach the link of our evangelist team on LinkedIn. So if you want to get connected to us, please welcome to swipe this QR code and reach out to us. We would like to share information on the progress of OpenVINO, and we would like to discuss any problems you may have when using OpenVINO. And here is the meetup Raymond just mentioned. We have this networking meetup on Thursday night. And welcome everyone to join us on Thursday night.
Register and then come. It's just a few blocks from here. On Thursday, it starts at 7 p.m.
Yeah. please just swipe this QR code and join us. Okay, finally, on September 24 to 25th, we will have Intel Innovation in California this year. As usual, we will in this conference to share some leading technologies from Intel. And also you can swipe this QR code for early access to opt in. And also we have the AI PC developer program to teach you how to use or how to build AI applications on AI PC. So if you're interested, also swipe this QR code to join our AI PC developer program. Okay, that's all for our fundamentals part for today's tutorial. Next, I would welcome Summit for the, I'm sorry, but our, our time is very limited. So I need to skip our break and welcome Summit to introduce the module 1 for OTX.
Thanks, Joel.
What else is, yes. What else is connected?
I need a USB-C.
Okay. You don't have?
No.
HDMI?
No, I don't. I need a USB-C. Okay, then I'll have to use this one from the shared drive, but I don't know how to.
have access to use the shared drive, only pen drive.
Pen drive? Okay, how's it gonna work then? Yeah, okay, I can do that. USB-C, I need a USB-C, okay. Cool.
Go back then with this computer. Just one moment, guys. We are trying to copy the deck. As usual, Mac cannot be connected. Don't use Mac, use Intel laptops.
In this case, I won't be able to do the practical demo.
That's bad. Module 1. Yep.
All right, can you hear me okay? All right, cool. All right, so far what we talked about is we have a ready-to-go model and we try to deploy that at the edge or on the edge, but we haven't talked about how we can train a model. So in this talk, I'm going to cover what OpenVINO offers to train a model if you have a data set that you would like to use that for a real world application. And that's going to cover all the way from data management to training or fine tuning for a downstream computer vision tasks and all the way to the deployment, basically. So if we start a computer vision, downstream computer vision problem, yeah, we always start with a data set, right? And today our talk will be covering the data set first. We're going to cover a zero-shot models to annotate a data set, like sort of an automated annotation, and Datomorrow, which is the Datomorrow the data set management tool that OpenVINO offers. And next, we're going to cover training and testing models, how we can utilize zero-shot segment anything model, or classification tasks, detection tasks, or segmentation tasks, which could be used like semantic segmentation or instance segmentation, basically. And the next step, once you have a model in a real world application, what you need to do is to export the model, as we've been talking about quite a while. And we're going to cover like the best known methods to know how to run this model. Also, OpenVINO training extensions cover explainable AI functionality as well, to see, you know, where the model is looking at. It's not like a black box, and to know what exactly the model is doing. And finally, we're going to be learning how to deploy, if it can show a demo. Right. As shown previously, OpenVINO training extensions is kind of a one-stop shop for you know, any sort of downstream computer vision tasks. We provide so many different tasks and models. It provides a CLI and API, and mainly because some people would like to, you know, some users prefer CLI just to run command line codes and subcommands with a couple of arguments, or some developers just prefer a really strong API for high, you know, lower level customization. So OpenVINO training extensions, shortly OTX, provide both of them. And the most important thing is the model optimization, inference, and deployment. Once we have a model that's good to go, that has a good performance, right? So it's all about end-to-end machine learning lifecycle, so that we can have a model that we could deploy. And our slogan is like, one command is all you need, because, you know, what we need to do here is just to provide some entry point subcommands with an OTX. So when you install OTX, it basically provides subcommands for each machine learning lifecycle or entry point, like train, validate, test, export, and so on. And we try to provide just one command for each of them and arguments. For example, here, if you want to train a detection task, you just say OTX train, provide the task, path to the data, and that's it. And if you want to do the same thing from API, basically what you need to do is just to import an engine, instantiate the engine, and call the train method, and it will train a detection task for you. And what is nice here is that when you provide the data to this engine, OTX decides what sort of data set is this. It's like is it a classification data? Is it a detection data or a segmentation data? And it sorts out everything under the hood. So you don't need to do anything. So that, you know, basically with a couple of lines of code, you can train the model with the corresponding task, basically. Right. So as I mentioned, it's kind of an end-to-end approach for the machine learning lifecycle, right? So it starts with the data and model, best known models, how we improve the models, how we optimize, and how we deploy. So when we start with the data, so we leverage Datomorrow, which is the front end of OTX, which provides so many cool features. If you want to, you know, explore the data set, you know, what sort of data set is this? How can I explore this? If I can find any, you know, noisy labels or anything like that. Or if you want to just convert a data set from one format to the other, let's say you have a Pascal format and you want a COCO or maybe some other. So there's tons of different options. So with Data Tomorrow, it is super easy to just, you know, do all these things. And once you sort out your data, what you can do with the models is that, you know, basically you can have you have access to any sort of models with different tasks. For example, here you can see that if you just list the models for detection task, OTX will provide you all the not all the, but many of the state-of-the-art algorithms that could be used for many real-world applications. And we tested those algorithms on many different use cases, and we ensured that, you know, it's not performing high on a certain use case, but, you know, fail on some other use cases. So it is all sorted out for users. So as I briefly mentioned, so we provide best known methods to run a model or a use the data set. And we also provide some approaches to improve like how we can improve this performance, right? So it's not like, okay, I have this model A, model B, whatever. It's not like, okay, it's giving me 60% of the performance, and what's next? So there are like already some recipes in the library that you could just use and improve the performance so that you can get as high performance as possible for your specific use case. And once you have, you know, this high performing model, statistically speaking, so the next step is what we've been talking about, basically, how we can optimize this model so that we can use that model on an edge device or on a CPU. Oh, nice. Right. And then finally, once we optimize this model, we can just deploy that with the inference capabilities that OTX provides. Right. Okay, so maybe let's jump into the features a little bit in deeper, so that then maybe we can start with the installation. So if you play with some of the well-known frameworks, you might notice that there's you know, you come across into like different sorts of installation issues, like, you know, you don't have the CUDA, or you don't have the CPU, or maybe just have mismatch, different drivers, and so on. So every time you just try to do that, and it could be easily just messed up even worse, and you might lose a day or two. I'm pretty sure that everyone experienced this sort of issues in the past. So we try to avoid this by providing a specific a subcommand just to install the library properly, installing the right version of Torch, you know, installing all these packages properly. So what a user needs to do is it's just do pip install OTX, and this will install a CLI, a really powerful CLI. And once we call the install subcommand, basically this install subcommand will do the rest for the user by finding the correct version of Torch, by just checking the system hardware requirements on the machine, and so on. So you don't need to worry about anything else. Right. So as I mentioned in the beginning of my talk, the OTX provides different task types and different learning methods, and many API CLI functionalities. And these task types cover many downstream computer vision tasks, all the way from classification, detection, rotated detection, segmentation tasks, anomaly detection tasks, action recognition, or visual prompting. And what's nice about this is that you don't need to worry about like switching from one framework to the other. So everything is in just one framework. Basically, using one CLI or one API, you can train different task types. in addition to this different task types, it is also possible to have different learning methods as well. So let's say you have a classification model, but you would like to, or maybe detection model, but you would like to perform a fully supervised approach or semi-supervised approach. So, you know, it would be possible to do this. And yeah, the additional functionalities would be like, you know, as I mentioned, the auto installation, auto learning method, integrated image tiling. Like if you have high resolution images, for example, you can just tile the images to focus and to be able to find, you know, the small objects to detect. Hyperparameter optimization to, you know, find out what are the best parameters for a specific use case. And obviously OpenVINO optimization just to be able to run the model as quickly as possible. And last but definitely not least, the integrated explainable AI functionality, where you can also have a saliency map that you can visualize for any of the predictions for each of these tasks. All right, so let me quickly go over the high-level architecture a little bit. So basically, we have a CLI here. That's kind of optional. As I mentioned, for those who would like to use the API, they can just use the API directly. But if you would like to focus on a CLI instead, yeah, that's basically the first step. But overall, the OTX has an engine, which is kind of the orchestrator that orchestrates all these workflow, and it consumes the data, which is handled by Datamaro. And we have this OTX models for each task, all the way from classification to segmentation and so on. And these tasks are run by PyTorch Lightning. We also have these OpenVINO models, of course, and the OpenVINO model API in case you would like to use these models on Edge, basically. And there is also support for other framework integrations as well, in case you would like to integrate your custom models from other frameworks into OTX. All right, so let me briefly talk about auto configuration. So let's say we have a data set, and these are probably, you might tell that these are images from Pascal VOC. And then you would like to use one of these tasks, like, you know, train the Pascal VOC data set on classification task. So what you can do is basically pass this data set into engine, and this has the auto configurator. So it will decide what task to run. And we have this data modules, models, callbacks, and matrix. So basically the data modules will sort out if it's an image data, if it's a video data, if it's our custom data, and so on. And the models, basically, is it a classification model or a detection model? Yeah, that's kind of handling that. And the callbacks are kind of the additional components that is not part of the core components. So that could be, you know, the timers or optimizers or any sort of extra stuff that you would like to add. And finally, the matrix. So we decide, you know, what is the performance of the model. So we pass all these into engine, and the engine orchestrates everything all the way from training, test, optimize, export, and, you know, to the deployment, basically. All right. So for example, for a CLI example, maybe, what we just need to do is call the OTX command with a train subcommand and provide the task. That could be, as you can see, many tasks here. It could be a multi-label classification, multi-label detection, instance segmentation, and so on, you name it. And pass the data as the data route. If you would like to overwrite some of these parameters, that's possible as well. So let's say you want to configure the CLI even further, not just, you know, with a few parameters, then that's possible. But let's say you would like to do this on using the API. Just import the engine and pass the data and the task to the engine, and the rest basically you can you have the option to train, validate, test, export, and all that stuff. It becomes quite high level. And as I said, what's nice about this is that you have access to all these different task types, not just one classification or detection, but all. Right. So in some cases, users might just prefer training or testing models from a configuration file. You know, these are kind of ready to go recipes, right? So you can just pick off the shelf and just use. So that's possible as well. So in this case, we can just pass the configuration file together with the data through CLI or API. And the configuration parser parses these sections, like, for example, the model here, we have efficient net here, and the engine arguments. And then basically the rest of the architecture is the same. So once we pass these arguments through the configuration parser, we can instantiate these data modules, models, and the rest of the components, and instantiate the engine, and the rest of the operation will be the same. So let's see an example how we can do this. Basically, if we want to use a CLI, again, we're going to be using OTX train. Pass the config, which is efficient net light YAML file in this case. You can just check it out on the repo. So these are ready to go off-the-shelf recipes, basically. And as I mentioned previously, let's say you already have access to this configuration file, but you don't want to modify this configuration file, but you just want to override some of the arguments. You can do that by overwriting these arguments by passing it from the CLI. Let's say you want to change the route to the dataset, pass the data route and overwrite, and change the data format to VOC or COCO, whatever. And also specify the other arguments that you want to change, basically. So that's the CLI bit. If you would like to do this via API, it is pretty similar to the previous example. So just import the engine, get the recipe from this path. So it is that there are a bunch of recipes already available that we tested on many different use cases. If you would like to override some of the arguments, so you can do that as well. And finally, just instantiate the engine from a configuration file, and the rest is the same. So just call the engine train. So you want to, let's say, run it for 2 epochs or 30 epochs, whatever epochs you want to try. And the rest of the arguments. So there's so many different arguments that you can tune here. If you're familiar with PyTorch Lightning, so whatever Lightning supports, the engine supports as well. In addition, it also has some extra arguments as well, so that it will give you the ultimate flexibility to train and test, any sort of models. Right. So far we talked about, the auto configuration, or maybe something, a recipe or from a configuration, but some users would just prefer the APIs, right? So in this case, they will just start with data modules, model, a callback, and the rest of the component, and instantiate the engine, and basically the rest of the entry points are the same. So we provide all the flexibility, right? So all the different options, different use cases, depending on the preference of the user, basically. So let's say I want to try the API modules from CLI. So you don't need to pass this config in this case. You can just start with the data and pass the, customize the data arguments, model arguments, engine arguments, all these components. It could be done from CLI. Sometimes it might be a bit difficult because if you want to tune so many different arguments. but it is possible. But let's say you would like to do the same thing from API, so you can create the data module from scratch, create the model from scratch. So let's say you want to use efficient net for multi-label classification, pass the number of classes. So, you know, just you have direct access to the API and pass these data modules and models to the engine. And again, you have the full control now. So you have all the orchestration all the way from training to the export, basically. So here, for example, I can just run this for 2 epochs, and I'm going to have a model, basically. Right. But these are, of course, OTX provides loads of other functionalities as well. It's not just these features. There's so many others. For example, custom data and models. So if you would like to use other models, not just the models that are already available in OTX, that's possible as well. Like, let's say you want to use some Torch Vision models or maybe some other models, Tim, or whatever. So it could be integrated. Image tiling, as I mentioned, it's, let's say you have a quite high resolution image and the objects are quite small. That in this case, when you train an object detection model, you'll probably miss all those small objects, which is quite common in industrial use cases. So in this case, what you can do is to enable image tiling and basically tile the images and train the model accordingly, so that you can focus on those specific object, a small object, without sacrificing you know, the small objects when you resize. So you lose a lot of information. XPU support, that's kind of the nice bit. So if you have an Intel XPU device, so the train and testing these models via XPU, yeah, that's also supported. So you just need to install the Intel extension of PyTorch, and then the rest of the stuff is supported. And let's say you have a model, but you would like to fine-tune the model by via hyperparameter optimization to find out what you know, what is the best parameterization. You can utilize HPO to do that. And I think afternoon, Alex will talk about more in detail maybe, but it is also possible to exporting to different precisions and so on. So you have the maximum flexibility. And finally, the optimization capabilities for, you know, the post-training quantization and so on. So these are all useful if you would like to focus on, you know, in a real world use case and would like, you know, the maximum flexibility to use the high performance models on edge devices. Right. So maybe I can talk about how we can do the custom data. So let's say you want to use some custom transforms or, you know, any sort of customization. So you can just basically customize that, and you have the full flexibility on passing that onto the OTX data module. So you have the training subset here, validation subset, and test subset. So whichever you would like to customize, all the way from data route to the transforms and maybe different formats, that's possible. Right. So if you have the custom data support, of course, the next one would be the custom model support as well. So let's say we can utilize other Torch Vision models. So we can do that via CLI. So let's say I would like to use ConvNext small model. So we can just specify the name of the model, and we can train the ConvNext small model from Torch Vision. And this will give us the, you know, the entire models and all of the OTX functionalities and capabilities all the way to the export. It is possible to do the same thing from API as well, right? So just import the Torch Vision model, and basically when you instantiate the Torch Vision model, this will create the OTX model, so you can basically instantiate the engine with the data and the model, and the rest, again, you have the full control of the pipeline, so you can train the model and, you know, carry out the rest of the tasks all the way to the deployment. Let's say you have a model, you have a custom data, custom model, but it is also possible that you can also customize your objective function as well. Again, this is for the control for the, you know, the full training pipeline. So you want to have a different loss function so that you can have a better training and so on. So what you can do here is, for example, you can just import the efficient net model, let's say in this case for multi-label classification task. And you would like to use this loss. Import that, and basically we can just pass the loss function to the model. And then this means that we can just instantiate the model utilizing this loss function. Again, the rest of the stuff is the same as long as we have this interface, so the pipeline is available. Yeah, we just train the model and that's it. So you have the full control and full access to all the rest of the capabilities. Right, so let's say we would like to do the image tiling. So what we can do is just to enable the tiling, and the OTX will do the rest for us. So it's that easy. For the API, again, that's also quite easy to configure. So we just pass the tile and enable the tiler here, and then the data module will sort it out. In terms of the XPU support, basically what we need to do is just to install by just providing the correct Intel extension, like the correct URL, and that's it. Yeah, of course, when we instantiate the train subcommand, we just need to specify what device we want to use, and yeah, the rest will be the same. Yeah, for the API, again, it's just give us the right the function the capability so that we can pass the XPU device to the engine, and then we can instantiate the rest of the entry points. If you would like to perform hyperparameter optimization, it's again just to pass the run HPO argument, and this will enable hyperparameter optimization. And if you would like to do this using the API, when you train the model, you set the hyperparameter optimization to true, and OTX will ensure that, you know, it'll run all the possible hyperparameter optimization or the arguments so that you have the maximum performance on a specific model, basically. Right, so if you would like to export the model, let's say you have the maximum performance that you can get from this data using the models that are available or your custom model, you can export it to different precision as well. Like if you want to do FP16 or whatever, so you just pass the precision to the export subcommand from the CLI, and that will be possible. And if you would like to do that from the API, it is just passing this precision to the export entry point to the from the engine, and that's possible. So I think what is most important here is that from the CLI and the API, there is one-to-one parity. So it's always you get the same behavior. So that's kind of one of the advantages of having two options, but with a one-to-one parity option. Yeah, so this is the optimization via NNCF. This is an example showing how you can do this optimization via NNCF, but I'm gonna probably skip this one to leave this room for Alex's session. But yeah, this is also possible to do that, basically. All right. I will try to set up my machine if I can do the live demo. We can do. Otherwise, I guess we'll have to stop here for the for the break.
Do you have any questions so far about the project? Yeah. Okay. So, see that OGS has a great story. 2 years ago, we tried to make a tutorial CPR about OGS.
Okay.
At that moment.
I'll just try to connect. I am having some connection issues. Let me just try it here.
Okay.
Yep. Right? Yep. Put it on, right? Yeah. All right. This is the practical demo part, but I think some connection issues. So when we found that.
Check, check. Check 1, 2. Check 1, 2. Check, check. Check 1, 2. Check 1, 2. Check, check. Check 1, 2. 1, 2, 3, 4. Check, check. Check 1, 2. Check, check. Good.
Story around retail and how we create with a simple data set that we have. How we can multiple kinds of computer stuff. So we have segment presentation. Of the detector. The library.
Oh, annoying. Sorry. Still having some connection issues, but we'll see. I hope you can hear. Okay. So. Right. So this is the practical demo, but it'll also require some training. So I need to connect to a server. I'm having some trouble connecting to the server. I'm not sure if it's because of this Wi-Fi here or the VPN or the latency, but yeah, there's some sort of problems. But I'm gonna be trying and running some Jupyter notebooks, but all those notebooks are available online. So I'll provide, you'll also see the QR code. So you can just check them out and they are all working fine. It's just a connection issue, basically. Hopefully we can go over them. So in this practical implementation, my plan is to go through the installation first. If I can do. Can you see that? No. How does that work? Yeah, okay, you can see this one. Is it too small? So let me try to connect to this workstation. Yeah, it's quite slow. Right. So, for example, here I'm going to be trying like installing OTX2. This is a virtual environment. So I'm just naming this as OTX2. That's the version 2. So let's see, we are on the right. Yeah, so I'm going to be doing pip install OTX, and it's going to be installing OTX. It might take a while. Meanwhile, we need, oh, Paul, you're going. So it'll install OTX, but the advantage is that it's going to install a bunch of packages to run on the hood. But the advantage is that it will give us a quite powerful CLI initially. And what this CLI tool is doing is basically, you know, in the slide deck, I was going through all these entry points, right? Install, train, validate, test, predict, export, all that stuff. So basically all the sub commands will be available after the second step, but initially it'll just provide us an install sub command. If we can see that, yeah, the internet connection is quite slow. So let's see. Okay, great. So so when we just do pip install OTX, basically this gives us the powerful CLI when we do OTX help. So as you can see, we can see this OpenVINO training extensions command line tool. And as I said, it's a really powerful tool, but currently what is available here is the install subcommand. And the main reason is that we don't want to install everything in one go. You know, this might be too long for people. And also, let's say if you would like to install this OTX on a small device, especially for inference purposes, but if you install Torch together with OTX, then yeah, you already have 2 GB and, you know, messed up the edge device already. So initially, when we start with OTX, we only have the install. But I'm having another virtual environment here already that I did the installation by just basically calling OTX install. Yeah, so when I do OTX help now, basically in this one, I called OTX install. As you can see, we have all these available subcommands here. So when we do OTX find, for example, it'll just, so it will give you all the helper functions and everything. So like, you know, if you want to find the models available for this task and that task, just give it a try. So you can have access to any of these subcommands and a quite powerful helper function as well. Right, so we have this that I showed you quickly. Maybe I could just quickly define the problem here. We just quickly created this data set to avoid any sort of licensing issues. But yeah, you know, this is a simple data set maybe, but you can just relate to any sort of real world use cases. So Ray was talking about some, you know, supermarket and retail problem that we've been trying to solve. But, you know, we can just think about this as like a self-checkout data set. You know, you just go to the self-checkout and place the items there, and then there's a camera, just, you know, find out what are the basically the things that you're buying. So think about it that way, in like a sample data set, basically. But what are the challenges in such use case? Obviously, the real-time scalability is one of the first issues that we're having, right? And the model performance, so we might need one model or maybe multiple models, and the performance of the model, like, you know, type of the task and so on. Let's say we ensured that we have a high-performing model, but the next step is how we're going to ensure that we have a memory-efficient model that we can run on a low-powered device. You know, when you look, for example, when you go to a supermarket on a self-checkout, it doesn't have a powerful GPU like this big, right? It's just like just a really small device that will perform the prediction. Right. So there could be a couple of solutions for this one, right? So we are approaching this problem from many perspectives. Like first one would be the zero-shot visual prompting. Why? We assume that maybe once we have this data set, we may not have the annotations, right? So the idea is initially maybe we can just utilize zero-shot segment anything model to annotate this data set, right? So that would be possible. So that's the first thing that we'll be trying, hopefully, if the internet connection will allow. But as I said, if you would like to have a look at it more in detail, the notebook is here. So let's try. Hope you can see this okay. We'll zoom in a little bit. Yeah, so I'm basically setting up the repo here, the OpenVINO training extensions, and downloading this data set. And for those of you who would like to have a closer look at the data, if I can see it. Yeah, it looks like this. So you saw the images from the presentation. Again, this is a sample data set. It's not super complex. So what we do here is to be able to run this zero-shot models. Basically, we specify the transforms here and we create the OTX data module on a zero-shot visual prompting task. I chose to use the API, but in the presentation, if you remember that, there could be many options. So you can do that from a config or from, the recipes and auto configuration, whatever. But here, we just choose to use the API version because I'm a big fan of the API and like to use the Jupyter notebooks. So once we set up the data, so we have access to the data module. So the next step is basically just create the zero-shot segment anything model. And the backbone would be the TinyVIT in this case. This is just to, to speed up the process to be able to quickly show you this example. Right. Once we have the data and the model, what we can do is, so this data module contains the train data loader, validation data loader, and the test data loader. So you don't need to, create all these from scratch. I basically get the data loader, and from the data loader, I'm just getting a batch of images. And then I will pass this to the zero-shot model and get the results. Right, so basically, once we have that, we can visualize the input image if the network allows me to do. Oh, right, okay. So this is the input image, and next we can see, okay, we saw already. Yeah, so we can see the segmentations. So the segment anything model already gives us a quite decent predictions. So assuming that, in this use case, we don't have the annotations, we can basically utilize OTX with a couple of lines of code and get the annotations. Right. Okay. Maybe try this one as well, if it works. Let's see. There's so much latency because of the connection, so. Okay. Yeah, so we have a segmentation for each object, basically. So as you can see, there's avocado here. We can see that here. And the broccoli here, and so on. I guess you get the idea. So we can just go back to hopefully the second one, if it loads well. Let's see. If it loads okay, I'm gonna continue. Otherwise, I'll probably need to stop. Okay, cool. Right, so let's go back to the slide. yeah, so this way we can, so this was just a one example and one of the tasks in OTX, right? There's not just one task, as I mentioned since the beginning of my talk. So let's say we did this and then we get some sort of data like annotated or maybe some predictions, but you know, we know that this is just a zero-shot model, and in some cases this may not just work well. And in such cases, in failure cases, we might need to focus on something else, like from a data scientist perspective. So the next step would be that maybe we can try a classification task, but since there are so many different objects inside this image, doing a classification task may not be a good idea. But maybe we can also do, we can just try multi-label classification. So in such cases, you know, in some cases, the customers may not just want to focus on the localization, you know, localize the object, but instead they just tell us that, give me the prediction. That's all I need. I don't care, you know, the exact location of the object. So in this case, we can do a multi-label classification. So as long as the model predicts that there is, you know, there's a lemon in the image, there's a banana in the image, there's apples and so on, that's fine. So we don't need to focus on the location. Right, so in such case, maybe we can try this here. Hopefully it will work. It's always hard to do a live demo. Right, I'm downloading dataset, but I already downloaded dataset, so I'm setting up. Yeah, so here we can see that OTX already provides so many available models. So that's the kind of the beauty of the framework. So let's say I list the models and specify the task multi-label classification, but I can specify any other tasks here I want. But in this case, I just list available models. You know, there's a bunch of models here. So, but in this case, maybe we can just use efficient net model, the B0. So it's already available here as a recipe. So if you would like to look at the details of the model configuration, that's also available in OTX. So everything is available. Oh no, it's trying to set up the SSH connection. That's not good. Right. So as I showed you in the slide deck, what we just did in this case, we just train the engine from configuration file, right? So remember there were like a bunch of different options. So this time we just choose to train it from a configuration file. So we don't need to specify it from the API by initially creating the data module and the model and so on. But basically we just use this recipe, train this from config for 30 epochs, and it'll just train it. Okay, it's done already. And basically, once we trained, it'll give us a model with pre-trained weights, right? And then we can just call engine.test, and it'll give us a 98% performance already with this amount of epochs. So let's say I would like to do explainable AI. Like I want to focus this time that initially, let's say the customer said, okay, I don't care about the location of the predictions, but this time they might just say, oh, hey, you know, this is a black box. Just show me some predictions, how the model is predicting. So in this case, we can just utilize the explainable AI option. Is it running? Right, I think it's running. I'm not sure. Ah, yes. Yes, latency is horrible. Yeah. Right. Okay. So what this engine.explain is doing is basically it goes over the test set that we have, and it's basically creates the saliency map for each individual image in the test set. And I'm setting the dump true here so that we can also save those saliency map into a file system, so we can have access to them. So let's say I want to see this image and the saliency map and the overlaid image. So what I can do is basically I can just read these images from file, because as I mentioned, I already saved these into the file system, so we have access to all of these artifacts. So this is the original image, and this is the saliency map, right? It's not great. So the model is performing well, but the saliency map is not so great. So what we can do, right? So in this case, we can say, hey, the performance is good, but I want some sort of localization. So in this case, I can switch the task, saying that okay, in this case, I'm going to train an object detection problem. Right, so let's go back to the object detection slides. But before, I think it would be good to load the detection Jupyter Notebook so that it pops up. Okay, nice. Right, so let's switch here. Right, basically, yeah, it's in this case, what I want to do here is just using the same CLI, same API. I would like to do, train an object detection model. So you don't need to switch from one framework to the other. So like MM classification to MM detection, for example. But just within the same framework, just switch the task. Right, so let's do that. Again, these are kind of the initial things that I need to set up. So we already have. Yeah, so in this case, I can do that from the recipes again, but if you would like to use the API, you can do that as well. So in this case, I just want to see what's available in OTX, and just getting the available models from the list models. And in this case, the only thing that changes here that I'm passing the detection task right now. And this will list all the available models for this task, for this problem, right? In this case, just to speed up the process, I just want to use YOLO-X model. And basically what I do is, here I'll show. So we have this recipe here. I would like to use this data model format for the data. Again, as I said, we can just configure it however we want, and instantiate the engine from a configuration file and train the model for 30 epochs. That's the idea. Let's see. Okay, so since this is an object detection model, this is going to take a little bit longer than the classification model. But it's still fairly quick, I would say. Right. Maybe we could have just reduced the number of epochs. So what's nice is that you can also visualize all these, train loss and the performance of the model on the validation set as well. So it's already doing quite well. Actually, I can just interrupt the model, but I'm pretty scared that I might mess up the connection as well. So let's wait. Right. Okay. So it's done. So what we can do is, as a next step would be just to call the test engine.test. Oh no, I hit the wrong. We need to retrain the model. But yeah, I mean, it is kind of, probably you get the idea, right? Hopefully if I clear all the outputs. Okay, so maybe we need 1 or 2 minutes to wait then. Yep. Well, for the training parts, no, everything is with Python, but we have the full OpenVINO model optimization support. So let's say once you train this one, so as you can see here, and once you're happy with the results, here we export the model. So export the IR model, right? So engine.export, and this will give you all this, the C++ capabilities and, all the OpenVINO capabilities that the rest of the folks are talking about for the, before my presentation. So you'll have access to all OpenVINO features if you just want to focus on C++. Okay. Right. I think it's done. So let's do the engine.test. So it'll, yeah, it just went over the test set, and as you can see, the F1 score is already almost 100%. But yeah, this is kind of a simple data set, but it gives us what we want. Again, if you would like to see how the model is, making the predictions, we can run the explain subcommand, and this will ensure that it'll go over the individual test set and then, get the saliency map for each test image in the test set and dump and save it to the file system, basically. Right. So let's see one image here. Yeah, it's much better, right? So when you compare it to a classification model, the saliency map wasn't great, but this time we have a good performance with an object detection model and also a nice saliency map as well, focusing on this stuff. But we can even do like one step further and then train a pixel-wise segmentation, right? So let's say this is bounding box around the object. This is the nature of detection task. But if you would like to do segment the objects, in some use cases, the customers want that, right? So what we need to do is basically just switch to the segmentation task. So it'll be something like this, right? Or if you want to do instant segmentation, it'll be something like this. Let's try to load the, oh, okay, it is fast. Right. Let's close this. Okay. So let's train a segmentation model now. So these are the initial setup things. Right. In this case, what I need to do is just to get the semantic segmentation, right? So that's the only difference. And again, the beauty of this framework. So you don't need to switch between frameworks for different tasks. I think it's 12 o'clock already, so this will probably be my final example so that we can go to lunch. Right, so as we can see, we have a bunch of different segmentation models that's already available here. So let's just run it from one of these recipes that we already made available for you. Oh, maybe I should have reduced the number of epochs to make it faster. But okay. Okay, so the rest of the logic is the same. Probably I can just show you some examples once the training is over, but maybe I can just meanwhile go over the rest of my slides if that's all right. So I don't want to take more of your time, like lunch break. So yeah, this is kind of what the segmentation and instant segmentation task will give us, right? So we will have predicted masks. But this is not kind of the only thing that you can do with OTX, right? There's so many other features that OTX provides. So if you want to do like image tiling or noisy label detection or fast data loading and all that stuff, or if you want to focus more on the algorithms, you can train a bunch of different downstream computer vision tasks. If you want, the semi-self-supervised learning approaches, that would be possible. Visual prompting, adaptive training, hyperparameter optimization. It's basically whatever you need for a downstream computer vision task, training and deployment. OpenVINO training extensions aim to make it available for you. So once you have this all data to deployment pipeline, and the rest of the OpenVINO inference, make all the OpenVINO features available. So the OpenVINO training extensions ensures that you sort out the data, train the model, to test the model, get the high performant model, export it, and the rest of the stuff will be handled by the inference capabilities of the OpenVINO. So I guess I'm going to be handing that over to my colleagues after showing the results of this. Hopefully, oh, you're not seeing that. Yep, okay. Yeah, let's see the test. Yeah, so we can see that we already have a good segmentation performance. Note that the performance dropped compared to the detection task, but you know, pixel-wise segmentation is more challenging problem. So I think it's okay to have this performance drop, and I would say this is a pretty good performance. And once we are happy with this, what we do is, as you just asked, yeah, I'm happy with this model. I can just deploy this on a self-checkout, retail, whatever. I export this model, I get the intermediate representation, and the rest of the stuff will be handled basically by the OpenVINO inference capabilities that we have. Right. Again, there's a connection issue. Okay. Again, maybe we can just show that, you know, once we export the model into, you know, the IR, one might expect that there could be some performance difference, but we can again check the performance of the model that we exported. So we can ensure that, you know, there's not much sacrifice for the performance or maybe the inference acceleration that we got. So we can just, you know, have the trade-off there. Yeah, so as you can see, there's no performance drop. So we have much faster model now that we can deploy, and we don't have any performance degradation. So that's what we wanted. Right. I think I can stop here. Maybe the long story short is that OpenVINO training extensions is a great framework if you have a data set and a computer vision problem that you would like to solve with different tasks, with different learning types, like classification, detection, segmentation, vision prompting, or different learning types, supervised, semi-supervised, and so on. And if you would like to if you don't want to stop there, just train and test, but also would like to deploy those models to use on an edge device, OpenVINO training extensions is the tool that you need to use, I guess. Thank you very much.
Hello, everyone. Welcome to the second module of our today's tutorial. In this module, I would like to share with you how to run a customized GenAI pipeline with LoRa and OpenVINO. So this is the outline of this module. I will quickly show a demo at first, and then we will dive into how to enable LoRa weights files with OpenVINO in 2 different methods, and then I will share some hands-on practice with how to run the whole pipeline. Okay, let me share a very quick demo at the beginning. All right, this is the this is the file I built this morning. And what kind of source codes I used to build this file? It is from our OpenVINO GenAI repository. So if you go to GitHub under OpenVINO Toolkit, you can find our repo here of openvino.genai. Inside this repo, we actually have a few tools and examples. As we mentioned this morning, we have benchmark for large language models, and also we have several examples of C++ for text generation and image generation. So for this part of the module for today, I would like to use the image generation as an example. And if you click here, you can find this one we will use today. That is the LCM model to generate an image. And so this is the source codes all included here in this repository here. And those are the steps, and those are the 2 lines of code that I used to build the files I'm going to share with you here. And to run it, because after building, I now have exe execution file. And so to run it, I can just navigate to the exe file. And then you can see I'm running with OpenVINO 2024.1.0 version. And with the default setting, because you can see I'm just running the exe file with no further configuration set. So I'm just using the default settings. I'm running the whole generation process on the CPU, on my CPU, on this laptop. And then after that, you can see the image has been generated and saved under this folder. And then let's open this folder and see how's the result. So it is saved in this generated images folder, and this is the one we just generated. Actually, the text prompt I sent into the default text prompt is a pink unicorn. And this is the result by using LCM to generate a pink unicorn. It looks not bad, I think. And so let's move on to see how we can use this pipeline to generate not only this image directly from LCM, but also with LoRa weights to obtain images with other styles. Okay. So speaking of LoRa, why do we need to use LoRa? I think you may have been familiar with the idea of LoRa, its low rank adaptation. Of course, as we see that the booming of large models, like large language models, large vision models, the number of parameters inside these models are increasing very fast. And so, as you can understand, the training cost for train or fine-tune such large models are increasing also very fast. So I think when we need to do some fine-tuning to the generally purposed trained models, it is easy to understand we need to find ways to reduce the cost in fine-tuning, in training. So that is the idea of LoRa became popular. Okay, a quick recap of what is LoRa. As we know that for a matrix like A with m rows and then columns, normally we say that the rank of A is equal to or less than the minimum of the number of rows or columns. And as we say that for the generally purpose trained large models, like large vision models, large language models, because they are trained for a very general purpose. So it's also easy to understand that to emphasize the task for a specific task or for a custom data set, we only need to pay attention or emphasize a group of the weights of these large models. We do not need to actually emphasize on fine-tuning all the weights within this large model, only a small part of it. And so it's not hard to understand here that we only need to change a delta weight of n times k, for example. So it means that for each layer, we only need to change a part of the weight on this layer, which is much less than the minimum of the rows and columns. It's a low rank matrix. And so since LoRa has become very popular in help fine-tuning the large models, but for today, we are not focusing on large language models. We're focusing on the vision models, the text-to-image vision models here. And you can see, actually, we now have some resources, open source resource that could provide the LoRa trained weights for text to image generation models. And those LoRa weights can be categorized on the concept they are trained. For example, they could be trained on the character, on the style, on the pose. And so if we navigate to the resource here, you can also find a lot of interesting and open sourced LoRa weights files that you can download and put into your Stable Diffusion or LCM pipeline to generate images with different LoRa weights to, oh. Okay.
Okay, now. Fine.
Okay. Anyway, you can open this civitai.com to find different styles of LoRa weight file there.
You want to put this?
Yeah, okay, I try.
Okay, you need to move this in.
Yeah. Oh,
Okay.
okay, great. You can find many interesting styles of LoRa weights here. And today I'm trying to show you how to, if you want to use the LoRa weights from this very different resources to generate different styles of images for you, how to use that together with OpenVINO to form a fast pipeline to generate such an image with those different styles for you. Okay. All right. So conventionally, if we want to enable the LoRa weights for the text-to-image models, we can do it using the diffusers library. So if you import the diffusers library and you load the pipeline, then how can you load the LoRa weights? We can use this API here, pipeline.unet.load attention process, for example, and we can load the LoRa weights here using this API. This is one way we can use diffusers to load the LoRa weights. And also, as we know, there's a very popular repository named A1111 for text-to-image generation. And if you're using that repository to generate image for you, we can also you can also using this this line of code to load the LoRa checkpoints from diffusers, like here. And so, as you can see here, today we are trying to show you a different way to actually load LoRa weights with OpenVINO. And why do we need to do that? I will show you in very shortly. But here, let's take a look at some examples first. To generate an image using the Stable Diffusion ControlNet pipeline, you can see here we actually need a few steps to run the whole pipeline. Of course, the first is to set up a virtual environment and then to do a model conversion, like to convert the PyTorch model into OpenVINO IR formats, as we mentioned this morning in our fundamentals, to help you to optimize and accelerate the whole generation pipeline. And then we will run the generation pipeline with our OpenVINO runtime. And here are some results. As you can see, if we input such an image with the Kenny image as our ControlNet model, and then you can see those are the two different generated image with Stable Diffusion and ControlNet. And here you can see we now can use OpenVINO actually to accelerate the whole pipeline. So of course, we can have some text input to control the image we want to generate. We can also input some image based on which we can generate the finally image we would like to see. And then after some safety checker, of course, we don't want to exhibit some results generated from typos or some maybe not inappropriate some text or words. So that's why we need a safety checker here. And then after that, this is the whole LoRa and Stable Diffusion pipeline, during which we can use OpenVINO to convert the model and accelerate the inference here. And so for here, you can see we can actually offload the different parts of this pipeline onto different devices to first to consider accelerate the whole pipeline. For example, safety checker could be performed on CPU. And for CPU here, we refer to different types of Intel CPUs like Atom, Core Xeon, or Core Ultra. And for those LoRa-controlled weights, we can put it on NPU or GPU. For NPU, of course, we mean the Core Ultra NPU. And for the whole Stable Diffusion pipeline in the middle with UNet, with VAE, something like that, we can also run it on NPU plus GPU. And finally, the safety checker, before the final output of the generated image, it could be performed on CPU as well. So this is the whole pipeline that OpenVINO can help to offload some of the AI inference workloads onto different hardware devices and then to accelerate the whole pipeline. Okay, next, I want to show you two different ways that we can enable LoRa weights into this whole pipeline with OpenVINO for acceleration. And the first way, we call it enable LoRa weights on OpenVINO in an offline mode. For the offline mode, we mean that we will use those several steps to enable LoRa weights. The first step is to load the Stable Diffusion pipeline, Stable Diffusion ControlNet pipeline from diffusers. Of course, that's in the PyTorch format. And then we will load LoRa weights. And finally, we will fuse LoRa weights with UNet. As we're showing here, you can see this is just, so for the first few lines here, you can see we just use diffusers to load the Stable Diffusion ControlNet pipeline from diffusers. Okay, so that is the ControlNet, and that is the Stable Diffusion ControlNet pipeline that you can already find on Hugging Face, right? And then after that, we can use load LoRa weights this way to actually load the LCM LoRa weights, and you can then use Fuse LoRa, this API, to actually fuse the LoRa weights with UNet to help you to form a new UNet that include the LoRa weights effect to help you to generate an image with the LoRa weight files here. And using those few lines of code, then we can fuse the LoRa weights with different styles with customized styles into your UNet. And then after that, we can run the original text to image generation pipeline, like run the text encoder, run the UNet, run the VAE decoder to finally produce an image generated with this pipeline. So those few lines in the middle are how we can actually fuse the LoRa weights in an offline mode into the whole pipeline. So as you can see here, the benefits is easy to see that it is actually easy to use because we just load the whole pipeline using the diffusers. Everyone is quite familiar with the diffusers library, so you can just easily use the original open source codes from diffusers, and you just fuse LoRa weights in the middle, and then you run the original pipeline. And when we say after that, we still want to use OpenVINO to accelerate the whole pipeline. Then after that, after loading actually the fused UNet, after loading the UNet, the BAE decoder, the text encoder, you can use OpenVINO to accelerate the whole pipeline with OpenVINO convert model. With the convert model, this API, to convert the 3 models into OpenVINO IR formats, and then use OV stable diffusion pipeline, something like that, using the Optimum Intel library we introduced this morning in our fundamentals to actually using OpenVINO to actually accelerating the whole generation pipeline. So as you can see in this way, it's simple, it's easy. You just use the diffusers API and to fuse LoRa weights into the UNet with only 2 lines of code. And after that, you can convert the models into OpenVINO IR formats and using OV stable diffusion pipeline to get the acceleration, to get the image generated more quickly than just using the PyTorch format. But I want to point out one thing here, that it is not hard to find that there are drawbacks in this method. So imagine you want to enable multiple LoRa weight files. If you want to infuse like 2 or 3 different styles into your finally generated image, how would you do that? So following the previous process we just show you here, you will need to fuse the LoRa weights once, convert them to OpenVINO IR formats, and then you need to fuse another LoRa weights, and then load the model, and then to convert them once again. So if you have multiple LoRa weights that you want to infuse into your final generated image, you need to fuse them n times, for example, and then to convert them n times. So that is heavy computation. So what we want to do is, if you have n different LoRa weight files, we only want to infuse them once. Okay, we only want to infuse them once, compile them, convert them once, compile them once, and to run the whole pipeline just once to generate a final image. So that's why we want to introduce the next method, which we call it enable LoRa weights in OpenVINO, on OpenVINO model in runtime. So compared to the way we just mentioned, it is an offline way. This way is what we enable the LoRa weights in the runtime. So it can achieve the effect that I just mentioned, that we can, especially when we enable multiple LoRa weights, we will only need to infuse the LoRa weights once into the UNet model and compile and convert and compile the model once to get the final results. So how could we do that in the runtime? The workflow is like this. So of course, first you have some LoRa weight files that are in safe tensor format. So first we need to extract the safe tensor files, and we need to create a dictionary list to save the LoRa weights layer name and the pairs of decomposition weights that we need to fuse the LoRa weights to the original UNet weight So we need to create this kind of list that we need to find the LoRa weights name, the layer name, and the decomposition weights that we need to fuse with the original UNet weights. And then after that, we need to read the IR models, which means that we need to read the UNet converted UNet IR models. And then the third step is to calculate the LoRa weights value using this kind of formula. And then you can see what we want to do is to add the LoRa weights to the original weights. So how can we do that? Here is the core of how we can do that. We need to create function to insert this LoRa weights into the converted OpenVINO IR formats UNet model by using the so-called OpenVINO runtime passes API. So in this OpenVINO runtime passes API, we actually call two functions. The first one, the first API is the manager register pass to register the subgraph insertion. So of course, first we will create a register subgraph insertion, and then we will call manager run pass to actually insert the LoRa subgraph into the UNet weights. And so you can see the whole process then is to load the LoRa weights and then to register the subgraph that we want to insert LoRa weights to and add them together to the original UNet weights and then do the further operation and compilation. And what happened behind the scene is that we can now call this function pass and the matcher pass folding together to create this inserted LoRa weights insertion result. And this folding together, this insertion is performed within the runtime. So it means that during the compilation, the performance will not drop in the runtime. And this one is a few lines of code that we actually defined in the insert LoRa functions. And you can see we actually use this OpenVINO runtime passes API to create this matcher pass function that can register and then start insert the LoRa subgraph into the UNet model. And first, there are some logics behind here. And the first is to filter out all layers that need to be converted or inserted, and then check if the layer name exists in the LoRa weights list. Remember, in the first step, when we extract the LoRa safe tensor files, we need to create a dictionary list to determine which kind of layers, weight layers, we need to insert the subgraph into. So here we will check if the layer name exists in this previously created LoRa weights list. And then we will create subgraph by OV offset and then insert the subgraph into the model here. And after that, that is finished for one weight layer. And then we will loop until all our weights insertion are finished using this callback function. So this is what we define inside the insert LoRa function. That is what we do actually to enable LoRa in the runtime way. And actually, as just mentioned, a more effective way to demonstrate that it's a good way is to enable multiple LoRa in the OpenVINO runtime. For example, if we have two LoRa weight safe tensor files, let's say we have LoRa A and we have LoRa B, and we can first calculate the LoRa weights using this formula here. And then we can first add those two LoRa weights together, and finally to insert the results after the LoRa computation into the original UNet model weights. So I want to use the comparison between these two figures to show you the benefits of doing this. So previously, if we don't do the enable LoRa weights in OpenVINO runtime, you can see when we want to enable multiple LoRa weights, what we do is to first calculate the LoRa weights and then insert them with the UNet model weights. And then when we want to insert another LoRa weights, we need to calculate once again to add, of course, to insert the subgraph to the results of the first inserted one. So if we are not doing this, we are actually running multiple times for insertion of different LoRa weight files. So of course, this one will bring some complications to complicated model graphs for insertion of different LoRa models. So instead, what we do here is we do everything of the multiple LoRa files, LoRa weight files outside the loop. That means we will first calculate the different LoRa weight files first by adding them together, and then reshape, add, build based on the results of the addition of different or multiple LoRa weight files. And then after that, we insert the result of multiple LoRa weight files together to the original UNet weight models, and then compile and running the rest of the operation and compile the model once. So in this way, we are only looping once for inserting multiple LoRa weight files. And here is one example. If we use A1111 of LoRa with OpenVINO to generate an image with different LoRa weight files inserted. So as you can see, we can use Stable Diffusion, Anime 1.0, this fine-tuned Stable Diffusion model with the ControlNet Kenny model. And then we can have two different LoRa styles, LoRa weight files, to be inserted into our pipeline. The first is the LoRa noise offset style. The second one is the LoRa soul card. So we can actually add or load multiple LoRa weights into this pipeline by using the steps we just mentioned. Okay, and also to compare the results, you can see this is the result from only insert one LoRa style, the LoRa noise offset, and this is the result from enable multiple LoRa effects, LoRa styles. And for the full source codes and more detailed explanations for this method, we provide you the Python source code, the C++ source code, and also a technical blog to explain how we actually do it in more detail. If you're interested, you're welcome to swipe the QR codes to try out the source code in Python or in C++. Or if you want to look for more information, you can find more information in our technical blog. Okay, next is our practical part. So here I want to share with you how we can run the overall pipeline I just showed you with the code. from our OpenVINO Gen AI repository, as I just mentioned. So the overall pipeline is working like this. We are using LCM, the latent consistency model, to generate an image. And our input is a text prompt. For example, we can input a beautiful pink unicorn as to generate this model, this image, and then we can we will use LCM IR models and LoRa weights to be running into our runtime to compile and finally to generate the image with different styles if we insert the LoRa weight files. And here I want to point out that for the source codes I shared with you on our OpenVINO Gen AI repository, you can see here we actually have this insert LoRa, this function defined for insert the LoRa weights. And so you can, with LoRa weights enablement, you can run the in the runtime to modify the model graph to insert the operation by adding the LoRa weight bias. And also we can support the runtime model graph modification by calling the OpenVINO Path API matcher interface. And also we can enhance the LoRa enablement loop of each layer by using the callback function. And as you can see here, we can read the LoRa weights in the highlighted part, and we can also support to different percent of LoRa weight effects. I will quickly show you a live demo, and you can see how those alpha number could affect the final result of image generation. Okay, so I will navigate to the path of folders that include everything for this demo. We are using the LCM Dream Shaper, this model for our demo here. And this is the my newly built files from this morning. And for now, I will just delete this one. And let's build from the scratch all over again. Okay, so to build from the scratch, you will need to follow our README from here. So basically, it's quite easy. It needs you to set up a virtual environment and install the requirements, install the packages from the requirements.txt file and to install another package, which we call OpenVINO tokenizers, to actually convert and export the LCM models from Hugging Face into OpenVINO IR formats. So these are the preparation steps that we need to before we building the final files. And then let's see, I have created this virtual environment, of course, and also I have installed the packages required in the requirements.txt. And then more importantly, I have pre-downloaded the LCM model from Hugging Face, and I have using this one command line to actually using Optimum Intel to download the LCM models first, then export the models into OpenVINO. And then I will point out that the export OpenVINO formats will be in FP16 precision. So after that, I will get in the models folder, converted LCM model into OpenVINO IR formats. And after that, all the preparation steps are finished. And then let's move on to build the final files to run the image generation. So this is the first step for the build. Okay, so now you can see the build is running. It takes me about 2 minutes to finish this step of CMake build. So I want to also point out that I'm using a VM from Python to set up my virtual environment here. And in our README on this repository, you can see you can also use Conda to create your virtual environment. So either way is okay. All right. So the first step of build is near the finish. Just need to wait a few more seconds to wait it to be finished. Okay, you can see the first step is actually finished now, and the time cost is about 1.5 minutes. And then let's build for the second step. So the compilation is working. Just need a few more seconds to finish this part. Okay, then this second step is also finished. So let's check our folder. Refresh, and you can see this is the one I just built by running those 2 steps of CMake. And then let's check what we can run with the compiled files. Okay, actually the compiled files, the build files, exe files are in this folder. And let's see what kind of parameters we can set to generate the image. Of course, we can configure the prompt here, and we can choose different device for generate the image. We can choose either auto, CPU, or GPU. And also we can change the steps that we use to run the LCM model to generate an image. So currently the default step is 4. And also we can change the seed number and also the number of images we can generate from running this execution file. And also we can define the height and width of the images we want to generate. And this here, as you can see, we can configure the type of this LCM models. And also here is we can load the LoRaWAIT files. And here is to change the alpha, which means we can change the how much the LoRa weight can affect our final generated images. And so let's make some changes. For example, let me change my device of running this generation to GPU. And also let me send a new prompt like a cute panda. And I want to generate perhaps 2 images. Then let's see what kind of images could be generated. So of course, the GPU would require some times to compile, but still it's quite fast that the images has already been generated. Let's check the images that save the results. So you can see now we have 2 cute panda images generated from the LCM model using the prompt I just gave it. And now, and here you can see we saved the images with the name of the seed it used. And then let's try to enable one LoRa weight files to see how LoRa works in this way. Then I will use this configuration to load the LoRa weight files, which I stored in models folder, which I use a soul card style. And let's see, this soul card styles of weight of LoRa weights can give us what kind of images we could generate for the cute panda prompt. Okay. Now you can see this is the same prompt, the same seed, but with the LoRa file, the soul card, this style inserted into our LCM pipeline. You can see we got absolutely different styles of panda generated panda pictures. Yeah, this is another one. This is the soul card style of LoRa weights. Okay, we also mentioned there's another parameter we can fine-tune, we can choose, that is how the LoRa weights could affect our final results using this, setting this different alpha value here. So by default, we are using 0.75. Let's increase the alpha number to 0.95. And let's see what kind of results we can get. Okay. Okay, this is the 0.95. That uses more biased or more LoRa weights infused or inserted into our original LCM UNet weights. So this is the result we get. Let's see if we want to lower the effect of the LoRa weight, what's the style we can get? Oh, okay. So this is more like ordinary cute panda generated images without this, like the so-called styles is more like a dark and maybe cool styles, and this is just an ordinary, because we set the LoRa weight bias to 0.25, which means the LoRa weight insertion or impact is quite limited into the final results. So you can see, by using those several steps, you can actually using our C++ samples to help you to build an execution file to help you to generate an image using LCM. And with the methods we just introduced, which means enable the LoRa weights on OpenVINO model in runtime, we can actually insert the LoRa weights, especially the multiple LoRa weights, into our pipeline more easily, and also cost less computation, because we actually insert the compute the multiple LoRa weights outside the loop for once, and then insert the added results, the final results, into the UNet weights, and do the compilation once. And if you want to try multiple LoRa weights, you can just list multiple LoRa weight files here after the L parameters. Okay, this is the hands-on part I want to share with you today. So I want to repeat here is that now I just show you that our runtime compiling can support the alpha % of LoRa effects. As you can see, if you set the number near to 1, it will set larger LoRa effect to the final generated results, because actually when we load the LoRa weights to our UNet file here, this LoRa weights is calculated according to the percentage of alpha we set for the configuration. And also the whole pipeline can be easily extended to support multiple LoRa files if you just add multiple LoRa weight files after the L parameter configuration. And as just mentioned, the whole hands-on practice, you can just follow 4 easy steps. The first step is to prepare the virtual environment by either Conda or through VM, and then the next step is to load the LCM model and install the required packages. And then by using the 2 steps of build, we can build the final execution file, and we can run the overall pipeline with different parameters configured, as just mentioned, as what I just shared with you. Okay, so for the conclusions of this part, I would like to mention that we actually introduced 2 ways to enable LoRa weights with OpenVINO. The first way is in an offline way. It is easy because it only need to add 2 lines of code using diffusers to fuse the LoRa weights into the original PyTorch pipeline. But the drawbacks of this way of enable LoRa weights is that if you want to enable multiple LoRa weights, it means that you need to fuse the LoRa weights n times and do the convert models and the compilation n times. So it means high computation cost. And if you want to use the enable the LoRa weights on OpenVINO in runtime way, then you can calculate the LoRa weights together outside the loop, and then insert the final results with our UNet weights once and compile the model just once. And so For the hands-on part, I would recommend you to try all the source codes from our OpenVINO.GenAI repository and navigate to the image generation subfolder to try all our source codes there. We have provided the C++ source codes there. You can try build one execution file from your own machine. Okay, that's all for this part. Thank you.
Any questions before the next module? Yeah. What is the most challenging part for the implementation of this pipeline with LoRa?
I would say we need to pay attention to the release versions of OpenVINO tokenizers, and also Optimum Intel to keep that to the latest version should work well after setting up the virtual environment.
Thank you, sure. So next session is module 3.
Are we planning to do like a break?
So starting at 3,
I'm like. Break.
I think that we can continue. Yes.
They should have some. HTML.
Resume, yes.
Yeah, I saw that. Yeah, we could have a break, but we can start now. Okay, I think we have like brave people here, right? Who like actually left. Thanks for coming. So my name is Alexander. I am a low precision architect of OpenVINO and responsible for model optimization direction. And the module 3, which is the last module in our workshop today, will be devoted to optimization of computer vision and specifically GenAI models using NNCF and OpenVINO. Actually, I would like to talk that I'm just an ambassador of the team of smart folks. You can see their names in the end of the slide. So all this team is small team, like working hard on the NNCF, on the development of the NNCF team, which is the model optimization toolkit. So here is the outline of presentation today. So first of all, we will focus on the optimization of computer vision models, why it is important. Then we will talk about some aspects of GenAI model optimization, because GenAI models, as you know, have some specifics. And then we will move to the practical part where we will like deep dive into the some API and examples of GenAI model optimizations like Stable Diffusion, some LLM models as well. And in the beginning, I will show quantization-aware training with Anomaly that was introduced yesterday. Okay, so let's get started from the computer vision model optimization. So why the optimization is important at all? Because like, I don't know, 5, 6 years ago, people just use models as is. right now it's optimization is a mandatory part of any deployment, because like most of the contemporary hardware has some special instruction sets dedicated to AI inference and the training as well. That's why it's important to reuse these instructions. Also, it's about like efficiency. Like if you use model as is, so it means that you underutilize or like underutilize instruction set or overutilize your hardware. So like to make it more efficient, to save money on the energy, so you can do the models efficient. And this is very important, like especially for the industry, where there are like sometimes there is a million of deployments of the same application, of the same hardware. Like you can think about sensors, I don't know, some cache machines, smart cache machines, smart, I don't know, TV screens, like advertisement and so on. So that's why if you save energy in like a tiny bit energy in some specific, in one installation, it means that you could save like millions of dollars when you do it at scale. That's why like constantly companies, like huge companies, come to us and ask about how we can optimize their models and like save some costs for them. And there are a lot of optimization methods available. So yesterday in the afternoon, there was a very nice talk from the Jabra, I guess, folks, who explained what kind of methods exist, right? But I think the one piece of information that was missed yesterday is about like how to apply these methods in reality. And like if we talk about the methods such as pruning, sparsity, narrow architecture search, distillation, I don't know, replacement of the blocks, and so like I don't know, like early exit. So applying each of these methods means that you should do a mini research anyway. First of all, you should have people who are knowledgeable in this domain, and then these people should do a mini research, because always it's like about the retraining the model and searching for the right hyperparameters, which allows you staying at the good accuracy performance trade-off. So that's why this method, definitely they are helpful if they're in the right hands, so to say. But if we are talking about the scale, adoption, and like easy of use, it's all about the quantization, because this is a method that is reliable. Everybody can use it. It's really not a big deal, and it delivers quite good results out of the box. So, and my talk today will be mostly devoted to like quantization of the models. So in the morning, Adrian introduced the quantization, what it is, how it works partially, but now I'm also gonna talk about this a bit, but at a different view angle. So first of all, quantization is pretty simple concept. But you know, there are a lot of tricks behind this. Even now, like in, I don't know, like 6-8 years ago, from when this method started extensively being used. So right now, there are new quantization methods which appears like every quarter, and every time people just try to apply them to like new models, try to find the better, let's say, precisions, better configurations, and so on. But in a nutshell, if we take a look at this simple 8-bit quantization, what it does essentially, so if we take a look at the most computationally extensive parts of the model graph, this is basically convolutions and matmos, like fully connected linear layers. So everybody knows what it is. And the dot product is the essential part of these layers. So if we speed up the dot product, it means that we speed up the whole operations. So, and if we take a look how the dot product formula, it's very simple. So what we're gonna do is we're gonna like approximate floating point weights and floating point. Oh, I don't have like pointers, sorry. Oh, okay. So we approximate FP32 weights with the integer counterpart, and FP32 activations the same way. So what we do, we quantize them like using any formula, but I don't provide it here, but it's just about dividing by this scale and rounding. That's basically it. The same for activations, right? What we can do next, we substitute floating point weights and floating point activations by the approximations. This is what is shown here. And then by simple manipulations and grouping, what we have essentially dot product that can be computed in int8, and we have superposition of two scaling factors, combination of two scaling factors. This is what essentially is called like dequantization. And now instead of computing everything in floating point, we can compute everything in the int8 and then convert back using dequantization, the group scaling factor. That's it. So the idea and concept is pretty simple. This is how it usually works in the runtime, actually. So, and for computer vision models, basically, there are two major directions how the quantization can be applied. The first is post-training quantization. When you freeze the model weights, you quantize them. You can do like some tricks to reduce quantization error, but that's basically it. It can be done even without data, but sometimes, usually actually, some calibration data set is required to do the domain adaptation. Because if you install the model in certain environment, you definitely need to fine-tune this model on the corresponding data. The same for quantization. In order to quantize the model accurately, you need to take data that corresponds to the domain, and you can do the quantization by estimating statistics for activations on this data. And this method, I mean, the post-training method, provides usually very good results in terms of accuracy. But sometimes where it's not enough, where it's or where like the accuracy criterion is so strict, quantization-aware training can be used. What it essentially does, it simulates quantization at the fine-tuning. And finally, after like 1-2 epochs of fine-tuning, you get the optimized quantized model that can be deployed. So, and like, yeah, so I have example also for this method, which I will show a bit later. So in OpenVINO at Intel, actually, we have a dedicated framework for model optimization. The framework is called Neural Network Compression Framework. It is a part of OpenVINO ecosystem. It is aimed at optimizing models specifically for OpenVINO runtime, so that these models can be seamlessly run on the CPU, GPU, and NPU, which is Neural Processing Unit. So and here is an example of the 8-bit post-training quantization API of the NCF that you can see. It's very simple, very intuitive. The most complicated part here is how to prepare your data. But here we also simplify this process by allowing passing like data loaders from the source framework. In this particular case, the data loader is a part of PyTorch, Torch Vision actually. So we instantiate data loader, and what we need to do is to write this transformation function. So what it essentially does, it just prepares the input for the model. It takes the data item from data loader and prepares the model input. In this specific case, it just drops the labels, because here data item is the combination of image and label. So we don't need labels because we don't do training here. We just need some images. That's why we take only images, and we wrap data loader with the helper class of the NNCF and pass it to the quantize nncf.quantize API. Everything is very simple. And after that, you get quantized model, which is in most cases pretty accurate. For the like very for some scenarios where the accuracy is highly important, it's actually important always, but some customers really tolerate some tiny percents of accuracy deviation after quantization. For those customers, we also offer accuracy-aware quantization. It's a bit more complicated API because it requires also a validation function to be written. But in many cases, if you take like publicly available models, they basically come with training code, right, and the validation code. So mostly you can take validation code from there, and based on this code, you can easily like adopt it to use accuracy-aware quantization. And what this quantization does, it just tries to find the most sensitive layers in the model, and it keeps these layers in the floating point precision so that your accuracy remains on the high level, and you satisfy the accuracy drop criterion, which is also like defined in the accuracy-aware quantization API. So regarding the quantization-aware training, it's we also try to make it as simple as possible. Usually, it's almost the same. It's actually the same process of model preparation as it's shown on the previous slide. So you need to like call nncf.quantize API initially. This is done for PyTorch model. And then what you do, you just fine tune the model for like a couple of epochs, and that's it. For this process, you can use the source training code from the PyTorch, let's say. And after that, the model can be converted to OpenVINO as usual, and that's basically it. But every time we recommend starting from the post-training quantization. So my colleague today asked me why we don't recommend starting from QET if it's more accurate. So my answer is simple, because most people don't train models. They just use models as this. So for them, even like if it's easy, if you like, for example, you can use Colab and available GPU resources on Google Colab or anywhere else. Anyway, like it's not that easy, because sometimes like if you take the public code, let's say, sometimes it's not reproducible. The results are not reproducible. I noticed this many times. So like researchers did the great job. They trained the model, but for some reason, if you like start the same code from scratch, you cannot get the same results. That's why you cannot rely on the like training code that much. And post-training optimization here is very safe, to tell the truth. And it's very easy. You don't need like GPU resources. You can do it on laptop even. Okay, so now we are moving to quantization of Gen AI models. and it's specific. So why it has specifics actually? Because Gen AI models are really, it's all about like large models, right? It's there is a term large language models. There is another term like large vision models. So it's all about like billions of parameters, and like my forecast is the amount of parameters will grow through the time, because we notice this grows like from the beginning of the deep learning era, when initially we had like maybe tens of millions parameters, then it's hundreds of millions. Now we have like billions and like hundreds of billions parameters. And probably we'll have like tens of trillion parameters. Because like if it, maybe it's like different, anyway, we have time, I can like talk a lot. But like if you take the human brain, and you know that in AI, most of the things are inspired by the human brain. In human brain, we have like 16 billions of parameter of neurons. And each neuron is connected in average to 5,000 of other neurons. And each connection, each synapse, actually, it's so the analog of the synapse is a weight in the AI model, which means that if we multiply 16 billions of neurons by 5,000 of connections, we get like approximately 90 trillions of synapses, or 90 trillions of weights. So I think we should expect something like this in the nearest future. But of course, it requires some hardware that can accommodate these such models, that can execute them efficiently. But in brain, it's sparse, so I guess we can expect some sparsity in the AI models in the future, some high level of sparsity. So again, large language models are really large. So before everything was compute bound, it means that the compute was a bottleneck when it comes to like model inference. Right now, since models are really large and huge, everything is memory bound, which means that it's not just about computing models. It's about like taking weights from the memory, bringing them to the local cache and to the registers, do compute, save results, and mostly it's just about memory, going back and forth from the RAM to local cache, and so on and so forth. And if you would like to optimize the model, you need to like squeeze these weights. And this is like where the most of the effort in the AI is dedicated to. And I will show like that just by squeezing the weight, you can increase the you can improve the latency significantly. Especially it works for LLMs, where the weights are highly dominated on top of activations. So, and again, if we talk about the like various optimization models, optimization methods available, so the only quantization, the only method that we can rely on. It doesn't mean that there are no other methods. Of course, there are such methods such as pruning, for example, or sparsity, but it's not like for like, you know, it's only for the researchers who know how it works and who have a certain amount of hardware that is capable of training such models. Because training LLM, for example, or stable diffusion, it's not the easiest thing that anyone can afford. And even quantization doesn't work out of the box. There is some specific that I would like to talk about. So again, if we look at the quantization methods like quantization aware training, it's hard to apply it out of the box to, let's say, LLM or stable diffusion, just because you need to train the model. And I don't know, like, how many people in the auditory trained stable diffusion or LLM. I personally did it like a couple of times, but it's not like that easy task. Especially if you're talking not about just fine tuning, but really the training the model. And like, if we consider how much data required for this, it's not just about the, GPUs, it's also about the storage. So that's why post-training quantization is a widespread method that actually pays a lot of attention of the researchers who are working in this direction. And so another problem is that for computer vision models, we quantize both weights and activations. Here, since we have like a lot of weights, like massive amount of weights, just by quantizing weights, we can improve the latency. So in practice, it works the following way. We don't use like, we can use like the floating point compute, but we still can quantize weights, and we fetched quantized weights from the memory, dequantize them on fly, and do the floating point compute. And by doing this, we don't hurt accuracy a lot, because actually activations is the part of the model inference which is highly sensitive to optimization and quantization. Weights are not. There is a lot of redundancy even in the contemporary models which are trained on massive amount of data. So that's why quantizing weights are quite safe. And when it comes to weight-only quantization, this is how it's called. So the benefits that are shown on the slides. So first of all, you can reduce the disk space and memory footprint of the model if you do weight quantization or weight compression. It shifts the model from being like memory bound to compute bound. It's also, as I mentioned, allows preserving accuracy, and you can like use even lower than 8 bits precision to represent the weights, and it works perfectly well, so to say. There are methods which can even squeeze weights to 1 point plus bit. So it's maybe looked a bit confusing how we can represent weights in 1 point bit, right? But there are methods which can indirectly like compress weights, like replace certain subsequences of weights to the indices in the lookup, and limit the lookup size so that you can have like decimal representation for the bit widths actually. But in general, so 8 or 4 bits are widely spread for GenAI model weight compression or weight-only quantization. And since, you probably know that most of the publicly available GenAI models right now, they available in the Hugging Face ecosystem, which is, mostly about the transformer library, which is built on top of PyTorch. In OpenVINO, we have Optimum Intel project, which is also a part of Hugging Face ecosystem. But what it does, it actually can convert model for you. You don't need to do anything, so you can just instantiate the classes from the Optimum Intel, and model gets converted from the transformers library to OpenVINO representation. And which is also important, it has an NCF optimization capabilities enabled, sometimes even by default. And here you have API for inference, but if you would like to go to C++, for example. We also provide the GenAI repository, as it was mentioned previously, which is about like C++. So in an NCF, yeah, so we have certain features dedicated to GenAI. As usual, this is full 8-bit model quantization, as it was for computer vision models, where both weights and activations are quantized. But you know that in GenAI basically it's all about transformer models, the models which have transformer blocks. For this kind of models, we have a certain quantization scheme, which allows quantizing models very accurately, just because some parts in the transformer block are very sensitive to quantization, especially if it's about integer 8 precision, for example. So that's why keeping them in the floating point precision allows reducing accuracy degradation significantly. We also have a smooth quant method enabled by default. I know that yesterday there was a session dedicated to this method as well from the Song Han and his team. We implemented this method as well. It works perfectly well for CLIP, stable diffusion, and you can also quantize LLM, fully quantize LLMs. And we also have a bias correction method, which is a kind of post-processing method, and it allows reducing quantization error introduced by quantizing weights and activations. But for this, you need the calibration data set. So for weight-only quantization, we provide 4-bit and 8-bit quantization of weights. We have data-aware and data-free quantization. Data-free is just about quantizing weights and minimizing the error without like considering data. But of course, data-aware methods are more accurate because they can consider the impact of certain data set, certain data distribution, and how it you know, how it affects the model inference, the output actually of the model. We also provide the AWQ scale estimation algorithm. This is our like novelty in the NCF that you probably cannot find anywhere else. So it's accurately finds the scales for the weights, considering distribution of activations. And we also provide the very famous GPTQ method, but actually you can use it like in any other third-party libraries because it's widely spread method. But which is the thing which is also important is that we can stack different methods all together. Let's say we can, for example, stack AWQ plus scale estimation plus data-aware precision selection. So data-aware precision selection is we find the sensitivity of the layers, how they actually impact the accuracy. And we assign, let's say, 8-bit to the most sensitive layers, while we compress most of the models to 4 bits. This is also important if you would like your model to be very accurate. So for diffusion models, we provide so-called hybrid quantization. This is the approach where we compress weights of the text encoder and the variational after encoder, the decoder part of it. And for UNet model, you know that attention UNet of stable diffusion consists of convolutional layers and transformer blocks. So what we do, we fully quantize convolutional layers, like we quantize both weights and activations. But for transformer blocks, we just quantize weights only. That's it. And it allows having very accurate results when optimizing stable diffusions. I will show the results a bit later. So and in the runtime, in the OpenVINO runtime, we also have dynamic quantization. It helps for LLMs specifically because, you know, since this is computer vision conference anyway, LLM now is a part of most of the contemporary pipeline, even like vision pipelines, right? So, and we also provide the quantization of KV cache of LLMs. This is purely runtime features. You don't need to do any preparation. You just specify the certain runtime property and the feature is enabled. I mean the dynamic 8-bit quantization and KV cache quantization. Okay, so looking at the NNCF API and translating all these features into the NNCF API. So this is 8-bit compression. It's data-free. It's super easy to use. It's just a matter of calling this function. That's it. You have an OpenVINO IR model instantiated in the Python API of OpenVINO. You call this API, and here you go. You get the optimized model. For 4-bit data-free, it looks almost the same. We just have two parameters here, additional parameters. First is ratio. It's a ratio between 8-bit and 4-bit weights. In this specific case, we quantize 80% of the layers to 4 bits while keeping 20% of the most sensitive layers in the 8 bits. And this is the group size, because usually, like if you go to 4-bit quantization, we quantize like certain group of weights with the same quantization parameters. It means that in this specific case, 64 values share the same quantization parameters, which is like scale and 0 point in this case. And for more accurate quantization, we provide the data-aware capabilities, which means that the user can instantiate data set as it is shown before, and pass this calibration data set to the nncf.compressWeight API. And NNCF will collect statistics. Moreover, you can now enable additional methods which allow you giving even better accuracy, getting even better accuracy, like AWQ method and scale estimation algorithm. And you can play with different sensitivity metrics that we also provide out of the box. So all of this allows us like quantizing even like very recent models such as Phi-3, Llama-3 with a tiny accuracy degradation. The model still remains very accurate. Like we tested this on, let's say, Phi-3, and like I can say that even on on complex reasoning tasks, the model still perform very well. So, but if you would like to get more performance, you can go definitely to full model quantization. It's when you quantize both and activations again, and the API looks the same as it was shown already. So all these features enabled in the Optimum. So you know that in the Optimum we have the same concept as in the transformer library, but with a different prefix. For example, for LLMs, it looks like OV model for causal LM. And again, the method is the same. It's called from transformer. But important part here that you can also pass quantization config into this from pre-trained method. And finally, you will instantiate like 8-bit model that you can save with save pre-train API, and you don't need quantize it twice. You can do it just only once, save, and then you can load it without quantization config, and it will be quantized already. So the same for 4-bit, 8-bit weight only quantization. So the same for data-aware quantization. All the options are available in the Hugging Face. So which means that this is just a matter of one call. That's it. And moreover, in this case, you don't need to care of the data set because we have some predefined set of data sets available. You just need to specify the string, what kind of data set I would like to use from the Hugging Face Hub. And the API automatically downloads this data set and uses under the hood. And for stable diffusions, we also provide the same feature. It's mostly like about, again, about specifying the quantization config that you would like to use. So everything is pretty simple and pretty scalable. So, okay, going to practical part. So like, I don't know how many people will like, yeah. So if anyone has questions, I'm happy to answer.
So is it a specific environment from memory to use an NCF? I mean, for making the.
Not from the NCF standpoint, but from the model standpoint, definitely. It's all about like the model that you would like to use. If it's a small model that I will show on the next demo from the anomaly, let's say, so you can do it in the collab or on the laptop. But if it's like, the huge model, so you can have problems with, memory, compute. It can take a lot of time. But it's all about the model, not about an NCF. An NCF is pretty small library.
I have a question. So for the quantization, you mentioned the weights only quantization. Do you aware any other like quantization method? I'm just curious because I'm just thinking to preserve the accuracy. Is there any other way that we can do the?
Yeah, sure. So there is a full model quantization where you quantize both weights and activations, right? And this method allows you getting the best performance improvement and best latency reduction. But if it's about like large models, so you can keep the activations in the source precision. This is important for the accuracy, because what is accuracy and what is activation? Activations is actually forms your output, right, of the model. So what is the accuracy? You take the output of model and you compute the metric. So by quantizing activations, you can like change output of the model more than if you quantize weights. Weights is something that you trained, and this represents the knowledge base that you got from the data set, and they are still redundant anyway. Like you don't need even like half precision for the weights. And in large language, in large models, large vision models, for example, the weights are really huge. So by squeezing the weights, you can still improve the latency, because what are you doing in the when you like do the inference of the model? So you take the weights, you fetch them, right? And then you do the compute. And since weights are much larger than activations, you need to fetch these weights more. And by squeezing them, you can save the like excess from the, let's say, registers to the memory, to the cache. And you can do like on the fly dequantization right before the compute. But compute still remains in the floating point. That's why weight only quantization is important. It still can provide you the good latency reduction, and you still preserve accuracy. But all the rest of the methods, like full model quantization, quantization-aware training, it can be also used. They can be also used, but still the application is still limited, because you have to be like the expert in this to tell the truth, especially if you would like to use quantization aware training, which inevitably involves the training of the model.
Yeah, thank you so much.
Okay, if no more questions, let's go to the practical part. Okay, so in the beginning, I have the environment set up, but actually each demo has its own, can have its own environment that you can use separately. So first example is dedicated to anomaly leap plus an NCF. So what we do here, we take the pre-trained model for anomaly detection. This is student-teacher feature pyramid matching model. It's a pretty simple model, but still effective. And since like anomaly detection is very, people usually use high accuracy when they would like to like detect anomaly. It's very important to preserve accuracy after optimization. That's why here we suggest using quantization aware training in this specific case, because as it will shown a bit later, the accuracy is very, very high after like quantizing and fine-tuning the model. So I have a Colab example specifically for this, where I will demonstrate, but actually the main example is located in the NCF. Okay, so just a second, yeah. So I just lost it a bit. Okay. You mean to Zoom, right? Yeah, this is an example that I'm planning to run. So what does it have? The most complicated part is how to prepare the data. Everything on top of this is pretty simple and looks like it was shown on the slides. So we extensively use AnomaLeap and its capabilities in this example. So what we define is some dataset related functions which load dataset and extract it. But again, we use anomaly for this. Then we also define some helper function which will benchmark the model, like estimate the latency improvement and the model size. And with this, what we do, we instantiate the model from the anomaly. This is anomaly helper. Then we create a data set using the function that we defined. And we also instantiate the anomaly engine, which reflects the use case. And since we have a pre-trained checkpoint, we also use it. We download it from the hub, actually. And what we do next, we estimate the accuracy of the floating point model. Then we prepare the quantized version of this model. If you take a look at this code snippet, it looks almost the same as it was shown before. So it's just about defining the transform function, which takes just image and drops labels. And it's instantiating an NCF helper for dataset. And then we just quantize the model. We take the model PyTorch module from the wrapper here. So it's actually the wrapper on top of the PyTorch, and this is a PyTorch module. So we take PyTorch module, and this is our model in this case. So we quantize it using the calibration set. And this is the models that we are gonna tune. So we just create a different wrapper. We set the quantized model as the PyTorch module there. And then we instantiate the engine for it, test the model after quantization, because this is essentially post-training quantization. And after this, what we do, we run the fine-tuning engine fit in this case. So essentially quantization of a training here is just calling post-training quantization and then calling the fine-tuning of the model. And that's basically it. Then what we do, we just export the model to OpenVINO IR because Anomaly provides these capabilities out of the box. We do it for original FP32 model and we do it for in-tape model. And then we run the benchmark. This is the function that we defined above. This function estimates the latency. Okay, let's try to run it in the Colab. Actually, I have everything run, but just to take a look how it works. Okay. So it's connected. For this, I use T4 GPU available in the Colab. But actually, it can be run on CPU as well. So yeah. So even in Colab, it takes a bit longer time, but anyway, it works in 20 minutes. You can get the results. With GPU, it's much faster. I think it can be done in like a few minutes. Yeah. So it's solve the requirements now. The most time consuming part here is to download the dataset. That's it. Okay, so maybe in the meantime I can maybe anyone has any question regarding the okay. Yeah.
Don't exactly how this algorithm works. I mean,
How the script works, you mean?
I mean like platform.
In this case, it's from Anomaly. I'm not sure. I think it's kind of mobile net.
Yes. So have a question. So, is it possible to combine quantization of a training and distributed training and mixed precision training?
Yeah, sure. So we provide in the NCF, we also provide the distributed training capabilities. Everything should work smoothly if you use it. Like if your script, like if your training script without an NCF is written in the way that it uses distributed training in the NCF, we also provide the calls. You can use like an NCF.distributed and it will allow like exchanging gradients between the different GPUs when you do the training, and everything should work smoothly. Regarding the mixed precision training, it depends on what kind of hardware you should use for this. Like, are you like asking about weight only quantization in the mixed precision setup, or
So like general question, both all model.
We provided, but like before we consider it like previous generations of NPU to use like mixed precision compute, but right now like this feature is not exposed, so to say. So in quantization and wire training, it's mostly about just 8-bit quantization. That's it.
Yes, okay. It's not trivial.
Yeah.
Really doesn't make sense.
So what we provide now is only 8-bit quantization in case of quantization of wire training. Another question?
If you quantize for the engine, what format do you return here? Is the PyTorch reference format or
It's a PyTorch model.
like other do insert a vector compile?
No. It's a PyTorch module. It's a Ego mode. Yeah. It's not like compile model. It's not effects. It's just eager model. That's it. We also insert some quantizers for activations because it's full quantization. Yeah. In the NCF, we did quite a lot of work by wrapping PyTorch before like torch effects appeared and so on, because this feature actually exists for 6 years and it's very tuned right now.
Like custom kernels for the
Yes, definitely. We have custom kernels for fake quantize to simulate quantization during the training. It works fast. They're written in CUDA. During the export, we convert them to like PyTorch native fake quantizers, which can be exported to Onyx or scripted. And for OpenVINO, we usually use Torch script. So we trace the model and we convert the script to the OpenVINO intermediate representation. The same for quantized models. The same for like source precision. Another?
If I just want to quantize, if I want to keep high precision of a specific layer, is that something archive achieving?
Yeah, that's for sure. That's a good question. So actually in the NCF.quantize, there are a lot of parameters which are not shown on the slide. And among these parameters, you can find ignored scope. In this scope, you can pass like a certain layer of the regular expression for the layer names. And all these layers which match to this expression, they will be kept in the source precision. So will be excluded from the quantization process. Assuming that you know what you are doing, like when you excluding these layers. Yes.
Well documented. So an NCF has its own repository, and you can find that information in the
I actually have another question. So just wondering, like, is there any like containerized environment that for this because it sounds like both environment is on my experience and kind of like sensitive to the CUDA version. I'm just not very generalized.
Yeah, that's also a good question. So in this specific case, we don't provide the Docker just because it's not like a single tool, right? It's an API. As you see, it's an API that should be implemented, which means that this API should be injected into some specific script. And it's up to you. If you like take the, I don't know, not just anomaly, but any other example of the model training, and if this example provides a Docker, you can use this Docker and you can just insert this NCF calls into the script. That's it. Because you can see an NCF is not like something that works standalone, right? It's specifically injected into this script, which fine-tunes the model. Because if you remove an NCF calls from here, what this script will do It will just fine tune the model. That's it. We're agnostic to CUDA because we use PyTorch to compile the kernels. And NCF doesn't, distribute it with a certain CUDA version, or because everything is written to be agnostic to CUDA. So like an NCF kernels are compiled on the fly when you first time access them. They compiled and cached. This is how it works. Like you install an NCF module, an NCF library. Like let's say you use an NCF.quantize, and when you first time use this API, the CUDA kernels will be compiled for your GPU and cached in this specific environment. Yeah, you don't need to to take care of that.
Does it support the pruning?
Yes, we have sparsity, like random sparsity. We have pruning. We have narrow architecture search. We have mixed precision, like everything, but it's not trivial to use. Because all these methods require the model training, not just fine tuning, not just simple fine tuning, but real training of the model. Because especially if it's like about LLM or stable diffusion, so if you inject 50% of sparsity, your accuracy degraded a lot. And you cannot do it in the post-training setup when you don't do the fine tuning of the model. You definitely need to train the model extensively. Okay. So, okay, we loaded the data, and now what we are doing, this is the accuracy of the FP32 model. It's very high, as you can see. Then right now we're quantizing the model. This is step 2. So what we do, we apply post-training quantization. We will measure accuracy after that, and we will fine-tune and redo the accuracy measurement just to see how fine-tuning helps in this specific case. You can see it. So we collecting right now. We collected statistics for activations just to estimate quantization parameters for activations, because weight distribution is available every time because it's just weight tensor, all the distribution available for you. But for activations, you don't know them in advance, right? You don't know all the data that will be passed to the model in advance. So that's why you need to estimate this statistically. Oh, you can see that we compile Torch kernels, CUDA kernels here, because this is the first time, this is a new environment. So we compile and cache them. We have CPU and GPU kernels. So now we are testing the 8-bit models that we got with post-training quantization. And in quantization, actually, validation is a most time-consuming part. It's not like quantization that works a long time. So it's just validation usually. You see that here we compiled CUDA kernels. It took some time because this is the first run. Okay, what we got, we have, so how can I change it? Okay. Our accuracy now is not that good as it was before. I can scroll up just to compare. Before it was 0.97, 0.90, 69.7%. Now it's smaller. And what we do, we fine-tune the model, fine-tune the quantized model. Okay, and the fine-tuning process finished, and this is what we have after fine-tuning. It's 1.0, 99.1%, 98.5, and even the last score is also increased. And this is a footprint of the FP32 model and INT8 model. And you can see that footprint is much smaller, like almost 4 times smaller, as it is expected. And now we're benchmarking the latency of the model. You see that this is footprint decrease, and this is performance improvement on when you run this on CPU available in the Colab. So it's 1.7x improvement in the latency. So this was quantization aware training. So let's go to the next example. Any other questions here? Maybe no. Okay, so okay, and as I mentioned, so LLMs now attract a lot of attention, and we also provide the features for LLMs that I mentioned above. And here I have example of all the types of quantizations that we have. It's a 8-bit quantization, but in this case. So in this specific example, we take the recently published Phi3 model. We quantize it to 8 bits using Hugging Face API, and we just do the inference to see the results. The same we can do for 4-bit quantization. It's actually 4-bit, 8-bit mixed precision quantization of weights. So this is ratio again means that 80% of the layers will be quantized to 4 bits, while other 20% will be quantized to 8 bits. So 80% of to 4 bits, 20% to 8 bits. And this is the last example where we will not just quantize weights, but we will also enable KV cache quantization and dynamic quantization of activations. This is done just by passing runtime config to OpenVINO. Okay, so let me open this example. I have it in VS Code, I guess. Yes. So, okay, this is, okay. This is the environment setup. Bigger, yeah. Have a good idea. I don't see. It's not displayed here. I don't see. You? Here is Control plus. Okay. It's okay now? Okay, so here is where we just infer the model in the source precision using the Hugging Face helper. So we instantiate the model. Actually, we do 8-bit weight compression by default, and this is where I cancel it. So I'm saying that I don't want to do like 8-bit quantization, just to remain the weights as is. So what I do, I just try to get the output for this question. Hey, model, tell me about LLM. And I measure the latency or average latency of the tokens, both like average it across prompt and next token generation. So actually, I run this example and it takes time. So I just would like to show the output and average latency per token. You can see that it's 0.23. Actually, it's 0.23 seconds, which is pretty slow, to tell the truth. And this is the answer that you can see, that you can read, I hope. Okay. And the first optimization feature, first optimization method is 8-bit weight quantization. So now I'm just passing quantization config. In this case, I could do nothing because 8-bit quantization is enabled by default. Again, so you see that the model was quantized, and now you can see the latency. Before it was like 0.23, now it's 0.08, which means that we improved latency like 4x, almost by 4x, just by compressing the weights from 16 bits to 8 bits without doing nothing. Like, it's a huge improvement. Just you can do out of the box. You can get out of the box. So regarding the output, it's almost the same. It looks the same, at least to me. So let's go beyond that and try like 4-bit, 8-bit weight quantization. Again, it's just a matter of defining the proper config here. The rest of the things are the same. Okay, so this is the output. Like you can see that 80% of the layers of the matmul operations were quantized to 4 bits, while 20% quantized to 8 bits, yes. And you see that we again improved the latency. Like before it was like 0.08 something, now it's 0.0664, which also like quite significant improvement. The output changed, but it looks pretty reasonable to me anyway. And this was, I guess, yeah, it was data aware quantization, but I didn't like use the most recent methods, which can take more time, but anyway, they improved accuracy, like AWQ, like scale estimation, for example. Sometimes it can take up to an hour just to get results. But once you get these results, you can like plug these options, additional options, and see how the accuracy changed. So, and in the last example, what I'm gonna show is that we take the model from the previous step, like 4-bit, 8-bit quantized model, and we just enable runtime options for dynamic quantization and KV cache quantization. And in this case, we can see additional improvement in the latency. Now it's 0.53. So compared to like FP16, like to the source precision, it's a huge improvement. It's like, I don't know, 6x or something, like 5x, I guess. But the output is different. It's still like reasonable. And again, there are ways how to improve it. And this is what we'll provide out of the box. Any questions related to this example? Okay. So, and the quantization actually and optimization, this is something that you can do just once, because you can save the model as it's shown here. Like we did quantization, which is time consuming. And finally, we called save pre-train model that you can use, because in the last example, what I did, I just used quantized model. Yeah, just that I saved previously. That's it. So no quantization happens. Everything works pretty fast here. All right. Okay, getting back to the slides. The next example that I would like to demonstrate is full quantization of CLIP model. So by full quantization, again, I mean quantization of both weights and activations. And CLIP model, as you know, it's an essential part of many pipelines, like stable diffusion, like just some zero-shot classification and even detection. So what I'm planning to show is how to apply the transformer scheme to quantize the CLIP model and using smooth quant method. So the example, okay, I have example probably also opened here. Yeah. This is the notebook that we have in the OpenVINO notebooks introduced a couple times today already. So I'm planning just to show the quantization part, because notebook contains quite a lot of code that demonstrates how to convert the model, how to, infer it, and so on. So I'm planning to focus only on quantization part and how it looks. Okay, so again, the essential part of the whole quantization story is how to prepare the data. And for this purpose, we use conceptual captions dataset available in the Hugging Face hub. You can see that we use a load dataset helper class from the Hugging Face here. And what we do, we just prepare the data items save them into in the list, right? And the data items essentially is just an input to the model. So it's a pixel values to the image related part of the clip, and input IDs and attention mask for the bird part of the clip. Okay, and what we do, we again prepare this. So we call prepare calibration data from this function, prepare data set, and we return the list of the data items that can be fed to the model. And now the quantization part looks pretty simple. So here we prepare data, load the converted OpenVINO model. This is OpenVINO model representation. And in this specific cell, we just call the quantization of API of an NCF using the an NCF.quantize API. So we take the calibration data that we instantiated before, we wrap it by the an NCF dataset. We don't pass the transformation function here because it's trivial. It's just take the item and pass it to the model as is without any like transformation of the data. That's why we can omit transformation function here. And we call an NCF API, and we point that this is transformer model. So for this, we have a dedicated parameter like model type. And we say that this is transformer, please use the special scheme for transformer optimization. And to make it more accurate, so we just brute force the smooth quant parameter here. We just, grid search over like 9 values, like starting from 0.1 to 0.9, and 0.6 provides the best results. This is what we used in this case. And once the model quantized, we just save it. And below you can see the difference in the results of the model. Sorry, so this is a clip. No, like you can see that model still in the zero shot scenario, the model still performs pretty well. This is the output, the score that this specific image contains dog. And if I scroll above, this was the original output of the model. You see that we have some reduction in the score that model provides after quantization, but again, anyway, it's still a high confidence that this is a dog. You can see. And the model size decreased significantly. You can see here, like it's since this is a transformer model, we apply the special scheme. The model is quantized very accurately, but the reduction of the model footprint is not that large because we still keep some layers in the floating point precision. But in this specific case, you can see that it's 2x of reduction in the model footprint. And in terms of latency improvement, after benchmarking, you can see that this is 1.64x of latency improvement. This is what I got on my CPU. Any questions regarding the full quantization of the clip? Okay. The next example is about stable diffusion model quantization. Actually, this is about LCM. latent consistency variant of Stable Diffusion. In this specific case, we quantize model, we quantize UNet only, but we fully quantize weights and activations using the transformer scheme again, because UNet is mostly consists of transformer blocks. And actually, we can quantize LCM accurately because LCM is pretty stable model. The reason why it is so is because the LCM is trained in the way to be stable. Like, because the intent of the LCM is like to stay consistent if there are any perturbations in the activations. So that's why we rely on this fact, and we not just quantize weights as it is shown a bit later, but we also quantize activations. This works specifically for LCM, and you can see very, very good results in LCM after the quantization, I mean. Okay, so let me open the notebook. It's again one of the notebooks that we have in OpenVINO notebooks repository. And it also contains quite a lot of code related to the model conversion, like wrappers on top of OpenVINO and inference. But again, I would like to focus on quantization part specifically. It will be more complicated than it was before. And again, the most complex part here is how to prepare the data for quantization. And since Stable Diffusion is not just one model, it's a pipeline of models. And we quantize UNet, which is in the middle. We need to take care of the inputs to the UNet. So how we do this? We create a decorator which just caches the inputs of the UNet. So it creates the data cache, which is essentially the list in Python. And when we run the inference of the UNet pipeline, it will take these inputs and cache them in the list. This is what we will use for quantization. So we define this decorator for the model that will cache the data, and we just run the inference over some data set. So we take the original pipeline, LCM pipeline, and we wrap the UNet by the decorator, which will cache its inputs. And then we just iterate over the data set, which again, conceptual captions, data set from the Hugging Face. Here is just simple loop over the data set where we'll call the LCM pipeline and we cache the data in the decorator. That's basically it. So all the code here just shows how to iterate over the data set and do some manipulations with parts of the LCM Stable Diffusion pipeline. And this is the most complicated part. Again, the quantization part is very simple. It looks like it was before. So we, okay, so we read the model. Yeah, in this case, we read just UNet model. We don't we don't take the whole pipeline. What we need, we just need to quantize UNet model, which is the most computationally expensive part of the Stable Diffusion pipeline. And we pass the subset of the data that we collected before. So, okay, this is how many samples we're gonna use, subset size, and calibration data set is something that we collected before. Again, we use transformer option because UNet is mostly about transformer blocks. And so we also did some tricks with disabling bias correction in order to, because it's not delivers good results in this specific case. So that's why this option is disabled. And we save the UNet model specifically, and you can compare. This is how this is the results of the optimized model. Before it was, let me show you how it looked. Yeah. It still looks pretty good compared to like the source model. No big difference. In terms of latency improvements, you can see like 1.32x in the latency improvement, which is maybe not that huge, but if you do like the generation all the time, if it's like the model that is served somewhere, it means that you can serve 32 more requests from the users, right? Which is quite essential part. Or you can use like 30% of the money if you like rent computational resources somewhere. Okay. And I think this is the last demo that I'm planning to show today. This is our very recent method for like general stable diffusion optimization. This is what we called hybrid quantization. Why it's hybrid is because we quantize most of the models in the stable diffusion pipelines in the weight-only quantization fashion. So like it means that we quantize weights only. But for the UNet part, what we do, we quantize convolutional layers fully. I mean, like both weights and activations. And for transformer blocks, we quantize weights only. And this allows us having very good accuracy, and still the latency improvement is quite significant. I will show in the dedicated notebook. So, and which is also important, it works well for most of the stable diffusions, not just for LCM. So in this specific case, I think we are quantizing stable diffusion XL. Let me. Okay. So, yeah, this is the notebook that we have in Intel Optimum, which again is a part of Hugging Face. So actually, Intel Optimum has the stable diffusion pipeline helper available for you. You don't need to write anything. And we exposed hybrid quantization as a part of the pipeline instantiation option. So here again, the most complicated part is how we collect the data. So what we are doing, again, we're using, I think it's again, now in this case, we're using Cocoa Captions dataset and stable diffusion 2.1. So we define the pre-processing function as it was shown many times before. And what we do, we instantiate stable diffusion. And there is a OV quantizer helper that user can use, and it is available in the Optimum. Actually, this can be done from pre-trained as well, because we just recently exposed this option, the hybrid quantization, as a part of from pre-trained method. So user can just pass this quantization config directly to from pre-trained. But in this case, we use the special helper quantizer, and it has also quantize function where you should pass the quantization config and calibration dataset, which just essentially takes prompts and just returns the prompts. That's basically it. And finally, after some quite a long time, because Stable Diffusion 2.1 is pretty heavy model, so we get quantized models that we save, and we compare it with FP32 Stable Diffusion pipeline. So in terms of visual accuracy, here are the results that you can compare. These are FP32 result, these are Int8 version. Like almost the same to me. In terms of model size, you can see that it's almost 4x reduction of model size, which is significant. And in terms of accuracy improvement, it's again, like in the LCM, it's almost 30% of latency improvement, which again, significant at the almost the same visual accuracy. I think it should conclude my presentation. Okay, on the last slide, these are some useful links that you can take a look. It's like weight compression examples again, it's a Hugging Face optimum and his documentation. It's OpenVINO GenAI C++. We are planning to highly invest in this API because we see that there is a lack of the C++, and this is what basically our industrial customers are using. They are not relying on Python. If it's like some, I don't know, models that are built in the firmware or into the operating system, it's about C++. If it's, I don't know, some industrial application, it's also about C++. And some benchmarks and interesting projects that you can find as well. Okay. There are 2 slides again, I guess.
For today, so we want to invite you for network meetup that we have on Thursday. It's just 5 minutes away from here. You can scan the QR code and register to the event. We have links for free on demos, and also you can, talk with different people. Not just in Intel, also OpenCV will be there. Boxer 51. We have some very good relations with some partners. You can, take advantage to have this conversation with them. And I think that also we want to invite you to the next Innovation event that we have in Santa Clara. That will be September 24th, where we also have a lot of showcases, how you can work, utilize Intel hardware and Intel software for improving your work. Yeah. So thank you, Alex.
Thank you very much.
Do you have any questions? So when you mentioned deployment using Python versus using C++, we know that industry uses a lot of C++. My question is, do you aware some of the applications the industry actually. I'm just curious.
No, it's like there are definitely some Python applications as well, especially if it's about serving or about like, I don't know, like on edge or on client deployment, it's mostly about C++. Or if it's about serving, model serving, remote serving, this is where you can use Python basically, and where Python actually dominates on top of C++. Like if the model being served somewhere. So it works pretty at the same, efficiency as C++. But if it's about like embedding some models in the firmware, this is where you need C++ API.
Question. So on end device production, that is.
Yeah, there are some Python-based applications that running on the, some like, how to say, some terminals, right? Where you can go like press some button or communicate with terminal if it's like AI model, right? So sometimes these are like Python-based applications as well.
Thank you, Alex. Just a little reminder, so you have access to the slides in the project page. You can access that, and also you can connect with all of us if you need or you have any questions in the future. Thank you.
Yeah, but